That's it. Thank you for your indulgence as we brought a few more chairs in. I appreciate the patience of those who are standing. The hearing will now come to order. Our hearing today is titled A Rational Discussion of Climate Change, the Science, the Evidence, and the Response. The purpose of today's hearing is to conduct an objective review of the science behind the greenhouse effect, climate change, and ocean acidification. My impression has been for some time that many members of the public and perhaps some in Congress have never had the opportunity to consider the basic science and, for that matter, the long history of investigation and data that underlies scientific understanding of the greenhouse effect and more recently of ocean acidification. Therefore, today we have three panels of experts with us. The first will begin today's hearing by setting the foundation of basic science. They will explain to us the fundamental physics and chemistry underlying the role of CO2 and other atmospheric gases in regulating or altering our planet's temperature and the acidity of the oceans. A bit of scientific history lesson will be included as we learn that the science behind this issue goes back more than 100 years. The panel will also address questions about how much CO2 has been entering the atmosphere, from what sources, and with what predicted effects. From basic scientific findings and methodologies described by the first panel, we will then consider whether or not the predicted impacts of CO2 on temperature and ocean acidity are in fact occurring. In other words, we will ask the question, if basic science makes certain predictions about what should happen if CO2 levels increase in the air and oceans, what is actually happening in the real world, how do we know if it's happening or not, and what can we predict for the future? The third and final panel will then discuss the impacts that are being observed and that can be anticipated from climate change and ocean acidification. Our witnesses will discuss how we are already responding today and actions we need to take to prepare for the future. The analysis includes such matters as national security, social impacts, economic effects, and health concerns, among others. I've had the opportunity in preparation for this hearing to read all of the written testimony. I want to thank the witnesses for taking time from their busy schedules to prepare this material and submit it beforehand for the committee analysis. We're also going to post that on the Science Committee website for those of you who are interested, and I hope you will be. It's wonderful testimony and very illuminating. Before we hear from the witnesses, I want to make just a few key points. Having taught scientific methodology and basic statistics, and having published myself in peer-reviewed journals, I personally place a paramount on scientific integrity. That is why, in the American Competes Act, I authored the provision that insists that institutions seeking to receive NSF funding have specific course training in scientific ethics. My understanding is from academia and from NSF that this is having a salutary impact, and I'm proud of that impact. I mention it today because, after all, this is the Science and Technology Committee. We must, if we are to have any credibility at all, insist that our witnesses adhere to the highest standards of integrity, and simultaneously, we members of Congress must hold ourselves and this committee as an institution to that standard in our study of the issues and in our conduct today and in the future. In the context of climate change and ocean acidification, I also believe that our nation is the biggest, because our nation is the biggest historical producer and second largest current producer of greenhouse gases, we have a profound moral responsibility to be sure we get this right. Scripture teaches us that to love thy neighbor as thyself. If our disproportionate impacts on the rest of the world are harming billions of other people and countless other species, we are not living up to that scriptural guidance. Finally, even if one completely rejects the evidence that will be presented today in reports from the National Academies of Science and countless other respected bodies, I believe it still makes good sense to strive for our nation to be a leader in clean energy technology for economic self-interest alone. Is not the reality of sending hundreds of billions of dollars abroad, often to countries with values antithetical to our own, at least a bit troubling for all of us? Is not the national security risk this creates disconcerting? Are the known impacts, such as Exxon Valdez, the Gulf oil spill, and numerous other events, not of sufficient concern to argue of change? And are not the facts of red alert days in our nation's cities in which it's unsafe for our children to breathe sufficient cause for some degree of consternation and change? I personally believe the evidence of climate change and ocean acidification is compelling and troubling. But even without that conclusion, I'm convinced we must change our energy policies for reasons of economics, national security, and environmental and human health. Our nation has long been a leader in renewable energy technology, and I believe we must remain a leader. This committee, under the leadership of Chairman Gordon and before him Chairman Bullard, have taken positive steps to ensure that continues. So, too, we've been at the forefront of climate research and should remain a leader there as well. We must continue this endeavor if we intend to leave our children and our grandchildren a strong economy and truly independent and secure nation and an environment in which to live, work, and play. Finally, as the parent of 5-and-a-half-year-old twin boys, the whole effort of my service in Congress and on this committee has been to ensure that they have a brighter and better future. If we don't address this issue well and responsibly, I fear we will fail in that mission and leave them a much less pleasant future than we've been able to enjoy. I'm excited about today's hearing and these three panels of witnesses. I thank them for their time. They will help us better understand the concepts and impacts of climate change, and I personally thank each of you for being here, and I thank our outstanding committee staff for their work in bringing such superb witnesses. And with that, I recognize my friend and colleague, Mr. Inglis, for opening remarks. Mr. Hall has to leave. Are you ready, Mr. Hall? I'm told you have to leave at some point, so... All right, then we'll recognize you out of respect for the likely soon-to-be chairman of this committee and a dear friend and a respected member. I recognize Mr. Hall for as much time as you.
Thank you, Mr. Chairman. Mr. Chairman, I do thank you for holding this hearing, and I welcome all the witnesses testifying on today's three panels. I think we have one witness for each panel, which is kind of an improvement. Usually we have one witness for each hearing. But 1 out of 3 is about a fair match, I think. Depends on the quality, but we're going to have a lot of different approaches to this and disagreements on it, and I appreciate everybody being here. Today our country finds itself at a crossroads, and we face a staggering national debt of more than $13 trillion. Almost 1 in 10 people are out of work and a bloated federal government. These are serious problems that require solutions that are defined by restraint and discipline. No longer should the economy be strained by writing checks we can't afford and a burdensome regulatory regime brought about by policies that serve to hamper industry and productivity across our country. Despite this economic reality, the administration is proceeding with regulations to reduce greenhouse gas emissions, a policy to supplant the, quote, cap and trade, unquote, proposal that failed to win congressional approval. The Secretary of Energy testified before this committee that such a policy would raise energy prices for every American. The Energy Information Administration conducted an analysis of the, quote, cap and trade, unquote, bill that passed the House in June. It was projected that this legislation would increase energy prices for consumers anywhere between 20% and 77%. The administration claims that we must cut our emissions of carbon dioxide despite the cost so that we stave off, quote, global climate disruption. Now, they've been calling it global climate warming. First of all, this new terminology pronounced by the White House Office of Science and Technology Policy is just another example of this administration attempting to rebrand events to suit their policy objectives. There's no more war. We don't have war now, according to them. Now we have what they say is overseas contingency operations, unquote. There are no more terrorist acts, despite that guy that murdered those people at Fort Hood. There are no more terrorist acts. We now have, quote, man-caused disasters, according to the administration. Let me tell you something. Changing the name doesn't change what it is. It's high time the administration learns how to call a bluebird blue. Secondly, this administration argues that cutting greenhouse gas emissions is a policy direction that's justified by the science. I think this hearing today will demonstrate and could demonstrate that reasonable people have serious questions about our knowledge of the state of the science, the evidence, and what constitutes a proportional response. Furthermore, there's been an escalating sense of public betrayal by those who would claim the science justifies these policy choices. The emails posted last November from the Climate Research Unit at the University of East Anglia in England exposed a dishonest undercurrent within the scientific community. This incident ignited a renewed public interest in the level of uncertainty of the scientific pronouncements and an increased concern that the policy of, quote, cap and trade, unquote, may not achieve its objective of reducing the impacts of climate change. While there are only a few scientists involved in this unethical behavior, it only takes a few bad apples to spoil the whole bunch. It's created a general atmosphere of doubt with regards to all scientific endeavors involving the government. We need only to look how the administration responded to the Deepwater Horizon oil spill to see how scientific information was distorted to promote a specific policy agenda or to change people's perception of the government's competence. To add insult to injury, this administration has neglected to follow through on promises to issue basic guidelines for scientific integrity, a failure that has only served to further erode the public trust. Given these persistent problems, Mr. Chairman, the public has even more questions and concerns about how federal officials use science to inform policy debates. Sorting scientific fact from rhetoric is essential, and we have a long way to go on this topic. We must insist on information derived from objective and transparent scientific practices, and we must hold this administration accountable for meeting the level of scientific integrity that the public expects from their government. Above all, we cannot afford to enact policies that destroy jobs, hinder economic growth, and whittle away our competitiveness. I look forward to hearing from our witnesses today, and I yield back my time.
Thank the gentleman. I'm pleased to recognize my friend and colleague, the ranking member of the subcommittee, Mr. Inglis.
Thank you, Mr. Chairman. And I think this is the last time that you'll be chairing a subcommittee. So I want to thank you for your service, and I hope everybody will join me in recognizing Mr. Baird for his excellent service here on this committee. So.
If I may, I'm going to interrupt my friend because it's the last time he'll be chairing or in the ranking chair, and he has been an outstanding partner to work with and a real model of a distinguished member of Congress. Please join me in.
Thank you. Yeah, there's a cautionary tale there about what happens when you get friendly with a Democrat. Actually, is a dear friend and a great guy. So I'm very excited to be here, Mr. Chairman, because this is on the record. And, it's a wonderful thing about congressional hearings. They're on the record. Kim Beazley, who's Australia's ambassador to the United States, tells me that when he runs into a climate skeptic, he says to them, make sure to say that very publicly, because I want our grandchildren to read what you said and what I said. And so we're on the record. And our grandchildren or great-grandchildren are going to read. And so some are here suggesting to those children that here's the deal. Your child is sick. This is what Tom Friedman gave me this great analogy yesterday. Your child is sick. 98 doctors say treat him this way. 2 say no, this other is the way to go. I'll go with the 2. You're taking a big risk for those kids. Because 98 of the doctors say do this thing. 2 say do the other. So, it's on the record, and we're here with important decisions to be made. And I'd also suggest to my free enterprise colleagues, especially conservatives here, whether you think it's all a bunch of hooey that we've talked about in this committee, the Chinese don't. And they plan on eating our lunch in this next century. They plan on innovating around these problems and selling to us and the rest of the world the technology that will lead the 21st century. So we may just press the pause button here for several years, but China is pressing the fast forward button. And as a result, if we wake up in several years and we say, gee, this didn't work very well for us, the 2 doctors turned out not to be so right. 98 might have been the ones to listen to. Then what we'll find is we're way behind those Chinese folks. Because, if you got a certain number of geniuses in the population, if you're 1 in a million in China, there are 1,300 of you. And you know what? They plan on leading the future. So if you're a free enterprise conservative here, just think, it's a bunch of hooey. It's science, a bunch of hooey. But if you miss the commercial opportunity, you've really missed something. And so I think it's great to be here on the record. I think it's great to see the opportunity that we've got ahead of us. And I also, since this is sort of a swan song for me and Mr. Baird, I'd encourage scientists that are listening out there to get ready for the hearings that are coming up in the next Congress. Those are going to be difficult hearings for climate scientists. But I would encourage you to welcome those as fabulous opportunities to teach. don't come here defensively. Don't come to this committee defensively. Say, I'm glad you've called me here today. I'm glad you're going to give me an opportunity to explain the science of climate change. Because I'm here to show you what you've spent, say, $340 million a year on the U.S. polar programs. So you spent the money. Now I'm here to tell you what you got out of it. And I'm happy to educate you on what the data is. And hopefully we'll have experts like some of here today, but also, you know, on a trip from this committee to Antarctica to visit with the money, the $340 million a year we spend on the polar programs. Met Donald Manahan, who's a professor at USC, the other one. We claim the real one is in Columbia, South Carolina, but the other one, you know, the one out on the West Coast. That one, Dr. Manahan is a master teacher. I hope he's one of the witnesses here, because he's the kind of guy that would welcome the inquiry and would lead a tutorial for folks that are skeptics so they could see the science. Meanwhile, we got people that make a living and a lot of money on talk radio and talk TV, pronouncing all kinds of things. They slept at Holiday Inn Express last night, and they are now experts on climate. And those folks substitute their judgment for the people who have PhDs and who are working tirelessly to discover the data. So we have some real choices ahead of us. But I hope in the future, as we have these hearings, that we realize it's all on the record. And our grandchildren and great-grandchildren are going to get to see. And it could turn out the science is all wrong. You know, we've had that before. We used to bloodlet people, and I think John Quincy Adams, the speaker, made the very helpful suggestion that we move him to the window, and the poor guy froze to death, right? They have to have the stroke over there in the Lindy Boggs room. So sometimes science turns out to be wrong, but other times it turns out to be very right. And the key to scientific endeavor is what we're here to discuss today, is openness, access to the data, and full challenging of the data. That's how we advance science. I look forward to the hearing, Mr. Chairman. Thank you for the opportunity.
Thank you, Mr. Inglis, for your opening remarks and for your many years of service in the Congress and on this committee. With that, it's my pleasure to introduce our distinguished first panel of witnesses, and I think Mr. Inglis's desire to have people who are thoughtful and critical analysts of data will be realized with this outstanding panel. The panel includes Dr. Ralph Cicerone, the President of the National Academy of Sciences, Dr. Richard Lindzen, the Alfred P. Sloan Professor of Meteorology for the Department of Earth, Atmospheric and Planetary Science at Massachusetts Institute of Technology, Dr. Gerald Meehl, Senior Scientist for the Climate and Global Dynamics Division at the National Center for Atmospheric Research, NCAR, and Dr. Heidi M. Cullen, the Chief Executive Officer and Director of Communications for Climate Central. Now, those introductions took me about 5 seconds to read each. If you read the distinguished biographies of these extraordinary individuals, it would take you 5 years almost to read. So forgive me for not going into such detail, but I hope you'll check them out on their website. You'll see this is indeed a very competent and capable group of individuals. As our witnesses know, we're asking you to summarize an entire career of research in 5 brief minutes, after which we will ask a series of questions. And this is the first panel. We have 2 other panels after this, and we'll do our level best to make sure that each panel gets a proportionate amount of time in our hearing today. And with that, Dr. Cicerone, please begin.
Thank you, Chairman Baird and members of the subcommittee, for the opportunity to participate in your hearing today. With your permission, I will present only a summary of my written testimony. Scientists have records from geological history of many past climate changes. For example, there is physical evidence of past ice ages with warmer intervals in between, and of a 100,000-year cycle of ice ages in the past. Volcanoes have also caused climate changes. For example, a worldwide cooling followed the June 1991 explosive eruption of Mount Pinatubo in the Philippines. Our ability to calculate the amount of that cooling is very high if the volcanic cloud material amounts and types are measured well. Natural climate changes are likely to occur in the future. However, the main reason that we are here today in this hearing is that humans are also capable of causing Earth's climate to change. The underlying mechanism is the greenhouse effect, wherein certain gases and clouds in the atmosphere surrounding the planet can absorb outgoing planetary infrared radiation. Each greenhouse gas selectively absorbs infrared radiation at specific wavelengths, and this signature can be seen by Earth-orbiting satellites and was indeed seen as long ago as 1972. The natural greenhouse effect has been enhanced by the increased amounts of greenhouse gases in the air due to human activities. These increases have occurred in a period of only a few decades, a very rapid change. The climatic impact of these greenhouse gases in the atmosphere is influenced also by changes in atmospheric water vapor and clouds that are initiated in turn by the warming. As water warms, it evaporates faster, in fact, disproportionately faster than the warming. Evaporation injects water vapor into the air. While some scientists propose that water vapor increases due to greenhouse warming might not amplify the original warming, they are fighting against a fundamental fact of physics, the steep dependence of vapor pressure of water, which is the Clausius-Clapeyron equation. The human-caused greenhouse effect exerts additional leverage on Earth's surface energy budget. The changes that have been observed in the last 3 decades, greenhouse gas concentration increases, temperature rises on the surface of the Earth, decreased ice amounts, can all be seen from space. In fact, that is how many of the data have been obtained, by looking at the Earth from space. The specific molecular properties of greenhouse gases have been measured through laboratory experiments so that the calculations of the enhanced greenhouse effect due to these increases in concentration are very quantitative today. The equations are the same that we use in designing nuclear weapons in neutron transport. The impacts of materials which are less uniformly distributed of various kinds is more difficult to estimate. A change in the amount of sunlight reaching the Earth would also be very important for the planetary energy balance, and scientists have proposed that changes from the sun are causing contemporary climate change, But recent evidence from monitoring the sun itself shows that the amount of solar energy reaching the Earth has not increased during the last 30 years, this time of clearly observed climate changes. Increased concentrations of greenhouse gases have been observed worldwide. For carbon dioxide, the data are of extremely high quality. Measurements are taken frequently from many locations on the surface, from aircraft, satellites, and from dated ice cores that extend back hundreds and thousands of years. Carbon dioxide amounts have increased from approximately 280 parts per million in the late 19th century to around 390 parts per million now, and that the increases are due to human activities is clear from several lines of evidence. Fossil fuel burning is causing approximately 85% of the rise, while the release of carbon dioxide from deforestation, perhaps 15% of the total. Methane has also risen rapidly in the last century, as evidenced from surface measurements of all kinds and from dated ice cores. Methane sources for the atmosphere include rice agriculture, emissions from cattle, the use and transmission of natural gas, the decay of organic matter placed in landfills, many human activities. Nitrous oxide, another greenhouse gas, also has an array of processes that injects it into the air, mostly traceable to the increased human usage of synthetic nitrogen fertilizer for agriculture. Several classes of chemicals containing fluorine are also contributing to the enhanced greenhouse effect, and these increases observed in the concentration in all of these gases are clearly attributed to human activities. Now some observed changes. Surface temperatures, both of air and of water, show a warming of the Earth in all regions. The globally averaged warming since 1980 is approximately 1 degree Fahrenheit. Stronger warmings have been measured in the Arctic region, along with differences season by season and locality by locality. Just as one example, the calendar year 2009 was significantly warmer than the long-term average in the northern hemisphere, but it was cooler than several of the previous years, while the temperatures in the southern hemisphere in 2009 were at a 130-year record high. Further temperature rises are are usually larger over land areas than over oceans.
Dr. Cicerone, I'm sorry, I'll ask you to summarize briefly if you
Okay.
can. It's always hard to keep it into 5 minutes, so.
The heat content of the oceans have increased roughly in accord with the calculated greenhouse effect, and sea level rise has been increasing more rapidly since the early 90s than had been observed earlier. And now we're in a position from measured ice losses over Greenland and Antarctica to sum up what's causing the sea level rise, and we got an answer which is in accord with the measured sea level rise. This is enormous progress over the last few years. A lot of continued research is underway. It's needed, for example, for quantitative calculations of where we go in the future. I'll just close by saying that the National Academy of Sciences has been active in our national efforts to understand these issues for over 30 years, and that in all of our reports we have always said that there's a lot more to learn about future climate change, but the potential for future changes, including sudden, abrupt, and large changes, is large. Thank you, Mr. Chairman.
Thank you very much. Dr. Lindzen.
Thank you, Mr. Baird. Oh, turn it on.
Yes. Thank you, Mr. Baird, and thank you, committee, for the opportunity to speak here. As a student, I was told something rather important, that the primary thing in solving a problem is to have the right question. And here, I'm a little bit concerned about the guidelines for this meeting. I think if we are to properly consider our concern over greenhouse gases, we must separate the basic science upon which there is great agreement from the specific bases for our concern. For instance, there's general agreement that climate is always changing. There is agreement that over the last 2 centuries there's been on the order of 3/4 of a degree centigrade increase in something called globally average temperature anomaly. There's no such thing as average temperature for the Earth. There is a greenhouse effect. Nobody is arguing that. That CO2 is a greenhouse gas is not argued by anyone I know. And that CO2 is increasing due to man's activities is also widely accepted. To be sure, general agreement hardly guarantees truth, but I'm not questioning it at this stage. But what is commonly forgotten, and that is crucial to this hearing, is that these facts do not lead to major climate concern per se. So, for example, doubling carbon dioxide alone leads to only about a degree of warming. And if all the increase in globally average temperature anomaly were due to the added greenhouse gases that Dr. Cicerone described, it would suggest a sensitivity that's even lower than that. The case for alarm rests on 3 rather doubtful propositions. One is that climate sensitivity to increasing greenhouse gases is much greater than the above due to the alleged dominance of positive feedbacks. The second is the association of phenomena such as sea level rise, Arctic sea ice, and so on, which depend on many, many factors, of which globally average temperature anomaly is not even the most important factor, and to use these changes as evidence for dangerous warming is illogical. This is especially true with Arctic sea ice. The oversimplification, this is the third item, of climate to a single number, globally average temperature anomaly, and a single forcing number, let's say radiative forcing from CO2, is a gross distortion of what is really going on. Now, with respect to climate sensitivity, greenhouse physics tells us that temperature changes at the surface should produce certain change in outward flux of heat, which at the top of the atmosphere is in the form of radiation. it will, in the absence of feedbacks, correspond to a sensitivity of about 1 degree for a doubling of CO2. Now, if you have positive feedbacks and you go to space and measure the outgoing flux associated with the temperature perturbation, you should see less than you would expect without feedbacks. And if you have negative feedbacks, you should see more. Now, it turns out that the models, when you ask what they calculate what is consistent with positive feedbacks. If you go to the data, you find the opposite. Most recently, there's been an attempt to measure these fluxes from the surface. Now, you have to understand, the flux might be reasonably constant through the atmosphere, but its process is different. So at the top of the atmosphere, it's radiation. At the surface, it's mostly evaporation. And there is a problem that has been noted for some years. Models predict very little change in evaporation as you warm compared to observations. And this can be directly translated into sensitivity. The model's behavior is consistent with 1.5 to 4.5 degrees for a doubling of CO2. The data suggests it's closer to half the lowest limit. So there too, I mean, one has the problem that the observations, when specifically turned to feedbacks rather than specific mechanisms, show the opposite. And this isn't surprising. One speaks of clouds as a kind of peripheral uncertainty, but they're capable, they involve changes in the radiative balance that are, more than a factor of 20 larger than what you get from a doubling of CO2. Now, parenthetically, we might wonder why models that have such high sensitivity can simulate past behavior if the past behavior is consistent with low sensitivity. And the answer, as I think Jerry would point out, is aerosols. Now, you might say there are really aerosols, so they cancel some of the greenhouse. But if you check, each model uses a different value. And the aerosols, because they want to adjust their model to look right, so it's an adjustable parameter. And the aerosol community, Schwartz, Rhoda, Charlson, and so on, have published a paper in the last year pointing out the uncertainties mean that if you include arbitrary aerosols, you can get any sensitivity you want. That's hardly reassuring.
Dr. Lindzen, I'll ask it.
Okay.
We're about a minute and a half over. I know it's hard to summarize, but if you can, I'd appreciate it.
Let me just point out that in my full testimony, there are examples, further examples of each of these things. The climate is certainly worth understanding better, but the basis for grave worries is poor. Certainly poorer than the changes of suggested policies, though perhaps not so poor as the prospects for suggested policies to significantly impact climate or even CO2 levels. Thank you.
Thank you, Dr. Lindzen. Dr. Meehl.
Thank you, Chairman Baird, members of the committee, for the opportunity to communicate information regarding processes involved with climate change, climate models, and extreme weather and climate events. But first, I want to begin with a personal perspective that I think is worth kind of stressing. I think that one of the most interesting, exciting, and challenging science problems, emphasize the word science problems, facing the research community today is the following. If you add greenhouse gases to the atmosphere, what is the response of the climate system? It is because of this compelling science problem that I find research in this area a fascinating and tremendous intellectual challenge, and it's why I'm here today. So anyway, the idea that additional CO2 and other greenhouse gases would cause a warming of the climate is not a new one. The so-called greenhouse effect has been studied since the late 1800s, and a number of simple calculations performed over the early 20th century indicated that a doubling of CO2 in the atmosphere would likely warm the planet by at least several degrees. However, a major development in this field of study was the emergence of numerical models that could be run on computers. Equations from fluid dynamics, physics, and thermodynamics can be used to simulate weather, and this had already been addressed early in the 20th century in a series of arduous calculations performed at that time by hand. It was not until electronic computers came into use in the 1950s that the equations could be solved in a rapid enough manner to be used for actual weather forecasts. This new science of numerical weather prediction became feasible for operational forecasts in the 1960s and is still in use today. Using the same principles and many of the same equations, early climate models in the 1960s were devised that could be mathematically integrated forward in time, much like numerical weather forecasts, but for much longer into the future. It was well known that after about a week, due to the chaotic nature of the atmosphere, the time evolution of individual storms could not be resolved by climate models. Instead, the climate simulations attempted to capture the statistics of weather over months, seasons, years, and decades. Since the climate models looked at weather and climate in this new way, other factors that could change slowly and thus affect the statistics of weather had to be included. Therefore, unlike weather predictions, where there was only an atmospheric numerical model, climate models had an atmosphere as well as components of ocean, land surface, sea ice, and equations that accounted for heating of greenhouse gases or cooling from visible air pollution. All of these components were linked together in one large computer program run on the fastest supercomputers available so that as much detail as possible could be included in the equations. These models account for physical processes and feedbacks, such as those alluded to by Dr. Lindzen, and these feedbacks involve water vapor, changes in snow and sea ice, and clouds, and of course all these affect how the climate system responds to changes in greenhouse gases. Some of the uncertainty of the range of model responses to increasing CO2 arises from uncertainties in these feedbacks, particularly clouds. However, climate models with a cooling contribution from negative cloud feedback still warm significantly on average over the 20th and 21st century due to the contributions to increased temperature not only from increasing greenhouse gases, but also from warming feedbacks involving increased water vapor, decreased snow, and sea ice. Since the end of the 19th century, global average temperatures have warmed nearly 1.5 degrees Fahrenheit. Many wonder why we should worry about such seemingly small increases of temperature. However, even small changes in average temperature produce very large and more noticeable changes in weather and climate extremes. It stands to reason that in a warmer climate there will be more very hot days and fewer very cold days. For precipitation, there is also a temperature-related connection. As more moisture evaporates from the warming oceans, the warmer atmosphere can hold that increased moisture, and when that moisture gets caught up in a storm, there is a greater moisture source for precipitation. Therefore, we typically see a greater intensity of precipitation in a warmer climate. That is, greater daily rainfall totals, or when it rains, it pours. Exactly these kinds of changes have been documented in the observations, namely more heat extremes and fewer cold extremes, and increases in precipitation intensity. Additionally, the shift to warmer temperatures has also produced an increase in daily record high temperatures compared to daily record low temperatures over the U.S., with this ratio currently being about 2 to 1. For example, since January 1st, 2000, there have been over 300,000 daily record high maximum temperatures set and only about 150,000 daily record low minimum temperatures set, a ratio of about 2 to 1. Just this year, since January 1st, 2010, there have been over 17,000 daily record highs and about 6,000 daily record lows, a ratio of more than 2 to 1. Thus, as the average temperature has warmed, the probabilities have shifted towards more unprecedented heat and less unprecedented cold. To a first order, climate models are able to reproduce these observed changes of temperature and precipitation extremes, thus building credibility for their future projections. Those projections of future climate change show ever-increasing heat extremes and reductions in cold extremes, ongoing increases of precipitation intensity, and a growing ratio of record-setting heat compared to record-setting cold. For example, in one model for one future climate change scenario, the current ratio of about 2 to 1 record highs to record lows increases to about 20 to 1 by mid-century and about 50 to 1 by late century. However, even in the late 21st century, when warming averaged over the U.S. is about 4 degrees C or roughly 7 degrees Fahrenheit net model, there are still record-setting daily low temperatures occurring. Thus, even in a climate that is warmed significantly in the model, winter still occurs, and it does occasionally get extremely cold in some locations, cold enough to set a few daily record low temperatures every year in that model. However, those few daily record lows occur in the context of many more daily record high maximum temperatures, and this is yet another aspect of a future warmer climate. Thank you.
Thank you, Dr. Meehl. Dr. Cullen.
Thank you, Chairman Baird and members of the subcommittee, for this opportunity to have a rational discussion on the science of climate change. I've got a PowerPoint which we are going to bring up, and it will reinforce several of the points that have already been made on the panel this morning. And I'll say that my background is a little bit different than some of my panel members in the sense that I spent several years at the Weather Channel as their on-camera climate expert, and it was a great experience, and it was really interesting to me because when I got there, most people just assumed I was a meteorologist, so I got a lot of questions about what the 5-day forecast would be, and while I love the 5-day forecast, it was a really important opportunity to just help people understand the difference between climate and weather, the difference between climatologists and meteorologists, and the difference between weather forecasts and climate forecasts. And if you see the great quote by Mark Twain up there, he basically said it all, which is climate is what we expect, weather is what we get. And I'll say, basically, it's a lot easier to see the weather. It's a lot easier to see what we get. Climate is a statistical construct, and it's tough to see it. So our job today is to help you see it and to help you understand why the forecasts that we make for the end of this century are something that we can trust. To start out with, Mother Nature's strongest fingerprint on our climate system is the seasonal cycle. So here's a climate forecast for you. Here in D.C., it's going to be colder in January, but then it's going to warm up in July. It's a climate forecast. My grandmother could give it to you. It doesn't take a genius, but it shows you that we have an understanding of our climate system that allows us to look further into the future. The other thing that I really hope that our discussion this morning can help you understand is why our long-term forecast for the future is something that so many of us on this panel are deeply concerned about. So I'm an engineer by training. I worked on Wall Street for a little while and then decided that I was really fascinated by climate. It has a lot, it's a lot like Wall Street in many respects. It looks kind of like stock market ups and downs on various time scales. And I'll say that the tremendous variability of the climate system is fascinating to me. And this GISP-2 ice core record here that you see, focus on the last 10,000 years. The top part, which is pretty flat, that's the last 10,000 years of our climate. And what's really fascinating is that it's relatively stable. And so what drew me into climate science was this question of, to what extent does climate stability link with human civilization? Because complex human civilizations started at about 10,000 years ago, right about the same time where our climate began to become more stable. So if any of you have read the book Collapse by Jared Diamond, you'll know that civilizations have failed over time due to the inability to look out on long enough time scales and to be adaptive to our environment. Now, my next slide is more or less to just highlight the fact that, gosh, we've been studying this problem for an incredibly long time. The gentleman in the oil painting is Svante Arrhenius. He got the Nobel Prize in Chemistry in 1903 for doing the back-of-the-envelope calculation that Dr. Meehl spoke about, which is if we doubled CO2 in our atmosphere, our planet would warm roughly 8 degrees Fahrenheit. Where Arrhenius made his mistake was that he was around at the turn of the century in the 1800s, and he basically assumed that we would continue to emit fossil fuels at the 1895 rate, and so it would take 3,000 years to double. So he was wrong there, but that's where Bert Bohlin came in. Bert Bohlin actually called for the creation of the IPCC, and he did his own back-of-the-envelope calculation, which suggested that CO2 would increase by about 30% by the year 2000. That turned out to be very true. Charles David Keeling, another giant in the field of climate science, basically figured out how to measure this invisible greenhouse gas we called carbon dioxide. We wouldn't need to have this panel if we could see carbon dioxide because it's everywhere. By burning fossil fuels and through deforestation, we emit it. But he figured out a way to create and build a machine that was like an atmospheric breathalyzer that could measure CO2 in the atmosphere. And he showed, just as Bert Bohlin calculated, that we've increased our CO2 in the atmosphere by about 36% now. We're at 390 parts per million. I know that does not sound like a lot, but because of the special chemical structure of carbon dioxide, unlike nitrogen and oxygen, which there is so much more of in our atmosphere, they have just 2 atoms. CO2 has 3, and that allows it to absorb tremendous amounts of long-wave radiation and be a great absorber of heat, and that's why our planet is essentially warming up. The other thing that Keeling was able to do was to chemically fingerprint the CO2 so that we knew that it was coming from us. Carbon comes in 3 different flavors. We call them isotopes. Fossil fuels, when they give off CO2 from burning, they have essentially no C14 because they're ancient. And so what Keeling was able to do was to say that roughly 1 out of every 4 carbon dioxide molecules in our atmosphere today was put there by us. It's our human fingerprint. on the climate system. As Jerry said, we are increasing the overall temperature of our climate about 1.4 degrees Fahrenheit over the past century. How does that make its way into our weather? My experience at the Weather Channel made it very clear that we can see our weather, we experience our weather, we know what that means. But how is climate change impacting our weather? Essentially, Mark Twain's quote can now be rewritten, which is to say that climate is what we affect and weather is what gets us. So we can expect to see more extreme events, and if you talk to, Warren Buffett or anyone who deals with insurance, they will tell you that if we don't take climate change into account, we are making very, very costly mistakes. We insure very, very high amounts of weather-related disasters each year. This is an example, a picture from the Nashville floods of 2010. It was considered a 1 in 1,000-year event. That probability is expected to increase more so with each passing year if we continue to emit greenhouse gases, business as usual. And just to summarize, I'm a scientist by training, and I have to say my time at the Weather Channel really, it just awed me the way our country could rally around a weather forecast. Whether it was sandbagging in advance of the Red River floods or evacuating in advance of Hurricane Gustav, we know what to do with a weather forecast. It's really impressive. And the thing is, how do we figure out how to respond similarly to a climate forecast? Weather forecast is all defense. We get the information, we've got to figure out what to do. With a climate forecast, the one difference is that we have the opportunity to change it because it is just one potential future. So essentially, when we think about the future, we're talking about an increase of 10 degrees Fahrenheit by the end of the century, 3 feet of sea level rise. It's a radically different climate. And the question is, if climate change is this ultimate procrastination problem, we're in a race essentially to understand our climate forecasts and just get to the point where we can act on them. And I would just say that as a scientist, if we don't do that, that would just simply be irrational.
Thank you, Dr. Cullen, and thanks to all of our witnesses. At this point, I'll recognize myself for 5 minutes, and we'll follow in alternating order as members wish to have questions. Just to start with a premise that I don't think often people appreciate, I don't think there's any disagreement on this panel, though I think I've heard disagreement by some of my colleagues occasionally. CO2 is essential to maintain the current temperature of the Earth. If it were not for CO2 or some other greenhouse gas, Dr. Lindzen?
Certainly understand, if you double CO2...
No, I'm not. That's not what I'm saying. Let me finish my question.
The current climate is mostly water vapor and clouds.
Okay, but let me finish the question. It is established science that the presence of CO2 in the atmosphere has an important role in maintaining the current surface temperature of the Earth and the atmosphere. If you did not have CO2, let me ask it this way. If we did not have CO2, would the Earth be a cooler place or a warmer place?
It would be approximately 2.5 degrees cooler.
Others wish to comment on that?
I think it would be a much bigger effect than that.
Hit the mic.
In the mid-1980s, Bob Dickinson and I did some of the earliest calculations of these radiative forcings. And Bob is one of the few geniuses in this field. And when he tried to do the experiment that you just referred to figure out what impact the current amount of CO2 is having, the calculations broke apart because the disruptions in the atmosphere were so large that he had to go back and start over. I think it would be far more than 2.5 degrees.
Let me ask the second question. Is there any doubt that CO2 absorbs more heat than oxygen?
No.
No doubt about that. Is there any doubt that the human activity has increased the amount of CO2 in the air?
No.
No doubt of that. That's a given.
How shall I put it? I would advise you to stop with the no doubt, but, that is the prevailing view.
Okay, fair enough. Okay, I'm a PhD scientist. I understand that science is never 100%, doctor, but I would say the prevailing view and abundant evidence suggests that humans have caused a substantial increase of CO2. Is that fair?
Yeah.
Okay. Now, here's the question. Is there disagreement with Dr. Meehl's analysis and Dr. Cullen's analysis and Dr. Cicerone of greater proportion of record highs in recent years relative to record lows? Each person will need to use their mic when they speak.
Yeah. I don't think they are meaningful statements. I mean, during this whole period he's referring to, if you look at it, it still looks like a random process, one, and two, the instrumentation has changed dramatically during that period, so that the response time of modern thermometers is almost infinitesimal compared to the ones used in the earlier part of the record.
Well, I'll rephrase my question because I think it was pretty clear, but your answer didn't address it. My question is there a doubt that in the recent years, and I'll state it as clearly as I can, there is a greater preponderance of record highs than record lows, unless you're suggesting that in the past the measurement devices were erroneous in one direction, not another.
Absolutely.
That's
because you have high response time, you'll pick up perturbations.
No, I'm not talking perturbations. Simply are we suggesting, Dr. Meehl, Dr. Cullen, if you're suggesting that the thermometers today are more sensitive to increases than to cooling?
Oh, yeah.
That's right. That's your belief.
I think that's pretty much true, but there's another issue here, which is a bit weird. Namely, why do we have record highs and record cold?
No, I don't want to ask the why first. I just want to get the facts. Dr. Meehl, Dr. Cullen, Dr. Cicerone, is it generally accepted, scientific fact, that there are more record highs today than record lows? Dr. Meehl?
Yes.
Dr. Cullen?
Yes.
Dr. Cicerone?
Yes.
Dr. Lindzen may disagree with that. Seems to me that that's a fairly objective piece of evidence that we could look at, that there are more general record highs. He may disagree, but I mean, part of what's happening here is that we have a preponderance of folks that, if I look at a temperature thermometer and I say, this is pretty hot, now other people could say it's pretty cold, but if we've got a measurement device we've been using for a very long time and it's showing a hotter temperature than what it showed a year ago, either the measurement device has changed or the temperature has changed. Now, maybe the measurement device has changed, but we're talking thousands of measurement devices changing, and only in one direction. Dr. Meehl?
Yeah, just to add a little bit to that, this analysis we did, we were looking at basically temperature records in the second half of the 20th century from weather stations that had good daily records, and this is actually, I think, a bigger problem than the thermometer problem, is that you have to have stations reporting their daily high temperature and daily low temperature every day, so you get to have a lot of daily records. And this ratio, which is now 2 to 1, which we thought was kind of odd. We thought initially, in fact, this came from a guy at the Weather Channel, because he was noticing this. He was keeping track of records just on his own. He's a meteorologist. And I was down there, Heidi invited me down there, and he said, what's with this 2 to 1 ratio? I said, I don't know. And he says, well, is that some kind of unique thing about climate change? I said, I have no idea. I said, let's look at it. So we started looking at it, and it turns out this ratio, we just happen to be at about 2 to 1 right now. A decade ago, it was a little less than 2 to 1. A decade before that, it was a little less than that. If you had a climate that wasn't changing, you'd expect that ratio to be about 1 to 1, because you'd have an equal chance of getting record highs and record lows. So I think what was interesting about that study is it showed, and I think this is a thing that we have trouble communicating to the public, but climate change is a shift in statistics. It's a shift in the odds of certain things happening. So as you warm the average temperature, you just shift the odds toward, you have a greater chance of extreme warm temperatures and a less chance of extreme cold temperatures.
Thank you.
And if I could just build on that very quickly, what Jerry did was he carried that thought experiment forward, which is part of the exercise that we all need to go through. And what they found was that if we continue to emit greenhouse gases business as usual, by the middle of the century, that would then become 20 to 1. So it gets worse as you move forward in time.
Because of the shifting of the probabilities.
Thank you, Mr. Chairman. I notice a discrepancy in some numbers here. Dr. Lindzen said that a doubling of CO2 would cause a 1 degree C increase in temperature. Doubling of CO2 would cause a 1 degree increase in
I said by itself.
By itself.
In other words, absent the feedbacks, and this the IPCC says also, you expect about 1 degree from changing CO2 from 280 to 560. You again get the same thing for a doubling from 560 to 10120. It's nonlinear, it's logarithmic, so every molecule of CO2 does a little less than its predecessor. But 1 degree is what you expect from a doubling. Anything more is due to the positive feedbacks from water vapor and clouds primarily in the models.
So I want to ask the others to say whether they agree with that. Dr. Cullen, I think I heard say, is an 8-degree Fahrenheit rise, right? So it's apples to apples.
No, the basic climate sensitivity doubling of CO2 experiment suggests an 8-degree Fahrenheit rise. That was the Svante Arrhenius calculation. IPCC estimates give a range, including all of the feedbacks.
So somebody help me explain that. Maybe Dr. Cicerone wants to try that.
Yes. What Dr. Lindzen is saying is if we could isolate the impacts one by one, the CO2 effect itself and the way it interacts with the planetary radiation would cause about a 1-degree warming under these circumstances, centigrade. It's the additional forcing, which I mentioned in my testimony briefly, of adding more water that causes part of the increased effect. Part of it would be due to the way clouds are being treated in the calculations also. But if I focus on the water, that's when I mentioned this disproportionate amount of evaporation increase as we warm a body of water. This is just a fact of physics. So that people who propose that this enhancing effect, which Dr. Lindzen denies, people who propose to deny that enhancing effect are fighting against a very fundamental part of physics. The fact that the rate at which a liquid evaporates is a grossly disproportionate function of the temperature.
May I respond?
Please.
What Dr. Cicerone is referring to is the Clausius-Clapeyron relation. That is a relation that tells you what the saturation vapor pressure is for water as a function of temperature. The atmosphere, first of all, is almost never saturated. So the basic physics that Cicerone is referring to is stating if you have a big bottle and somebody has this cup, no matter what I've done to pour water into each, this will always have more. That doesn't make much sense. But the other thing is the data I referred to.
Let me stop you right there. What does that mean? Dr. Cicerone, what is your response to that? What is it?
I didn't follow him. I know the Clausius-Clapeyron equation. I know its basis. You need to hit your mic. I know the relation he's speaking of. I know the relationship with the entropy and thermodynamic quantities, and I don't understand what he's saying.
I'm saying it's for saturation vapor pressure, right?
Yeah, sure.
Okay. Is the atmosphere saturated?
No, we have a more or less relative humidity on average of 70%.
Yeah,
Yeah.
fluctuating all over the place.
Yeah.
Clausius-Clapeyron tells you nothing about that.
It gives you an approximation to the slope.
Both gentlemen to use your mics.
Okay.
We can get an approximation to the slope. That is the way the
Turn your mic on. Go ahead and leave it on.
All right. The way the evaporation takes place can be also approximated by the thermodynamic quantities that give the slope of the relationship, and it's just a rapid increase. It's very hard to hold back the vapor pressure of a liquid against this relationship, whether it's evaporating into gas above it that's saturated or not.
Yes, Dr. Meehl.
Well, yeah, I was just going to add that this quantity we're talking about, which is an equilibrium response of the climate system to a doubling of CO2, actually has a history to it that goes back to the early days of climate modeling when that's about all you could do would be to double the CO2 and then see what happens. So it's ended up being this kind of equilibrium climate sensitivity, and that actually goes back even earlier than that. We will never actually see the equilibrium value because it takes so long for the oceans to catch up. So this is kind of a metric we use to give us a rough calibration of how the climate system may respond. So these are kind of relative numbers. But I think maybe the point is that there's a range of what we think this number may be. The current range we think is anywhere between 2 degrees centigrade and 4.5 degrees centigrade. And this number was derived a lot of times from models, but now we have multiple lines of evidence, people have actually looked at observations, they've looked at the response of the climate system to big volcanic eruptions, look at paleoclimate data, and so now we have multiple lines of evidence that seem to suggest that that's probably about the right range, and that the most likely value is actually around 3. And I think Dr. Alley is going to say a lot more about this in panel 2.
Thank you. Thank you, Mr. Chairman. I'm out of time.
Dr. Bartlett.
Thank you very much. This hearing today, I think, is one of the more important things that the Science Committee needs to do. There should be no dispute as to what the facts are relative to climate change, and there's a lot of dispute as to what the facts are. There can be a great deal of dispute as to how you interpret those facts. But we really need, before you can have an honest discussion, you need to agree on the facts. We don't now agree on the facts, and so I really appreciate the chairman holding this hearing and thank the witnesses for their contribution to this. The chairman's question, if there was no CO2, would the Earth be colder? Not if there was just a little bit more water vapor, because water vapor is a hugely more important greenhouse gas than CO2. I know the chairman meant that if all other things remained equal, would the Earth be colder if there was no CO2, and of course it would. But CO2 is a pretty small greenhouse gas compared to water vapor. That doesn't mean that it's not important, because it can be the tipping point. There are 3 groups that have common cause in wanting to reduce the consumption of fossil fuels. And regretfully, they are at each other's throat rather than joining hands and marching forward. One group is a group that is represented today, those who are concerned about climate change and the effect that the CO2 produced from burning fossil fuels would have on that. A second group is a group that is really concerned that the United States has only 2% of the known reserves of oil in the world. We use 25% of the world's oil, and we import just about 2/3 of what we use. And the solution to that, obviously, is to stop burning so much fossil fuel and use alternatives, which is exactly the same solution that we have today in looking at the effect of CO2 on climate. We'd like to produce less of it by moving to alternatives which do not produce CO2 if you have a short cycle rather than a million-year cycle like we have in fossil fuels. And the third group that has common cause in this, and I just happened to have a paper this morning, it just came out, the world's energy outlook for 2010, now out. And I will try to have this thrown on the screen later today because it is really a startling picture. It shows that we have now peaked in conventional oil production at about 65 million barrels a day. The total world production is about 84. The rest of that is made up of natural gas, liquids, and unconventional oil. This chart has that plummeting to about 15, only about 15 million barrels a day by 2035. That's just 25 years from now. And it has the difference made up because they have plateaued essentially with production of oil. And the difference is made up, and it's, I think, about 42 million barrels per day they say that we're going to get from fields yet to be developed or found. You know, that's the impossible dream. That's not going to happen. Now, the solution to this problem, the fact that the fossil fuels just aren't going to be there to burn, is to move to alternatives. And so whether or not you are right that the increase in CO2 is producing climate change, there are two other very good reasons for doing exactly what you want to do, and that is to move away from fossil fuel use to alternatives. Why aren't these 3 groups locking arms and marching together? Because they have exactly the same solution to very different problems. What keeps you from doing that?
I think the 3 groups have locked arms and have moved together, but I think there's a lot of opposition. I think it's a very difficult thing to change one's invested infrastructure. And I think much of the discussion about climate change and alternative energy is making that leap and moving forward and embracing new technology. So, can we do a better job? Absolutely. But I do think that our 3 communities have aligned and it's clear that there's multiple reasons to shift away from fossil fuel.
Even if your premise is not correct, that is, that human production of CO2 is not changing the climate, what you want to do about it is exactly the right thing to do for two other very good reasons. Again, I ask, why do not these three groups, instead of sniping at each other's premise and ridiculing each other, why don't you just lock arms and march forward? Because the solution to these three very different problems is exactly the same solution. Less fossil fuels and more alternatives. Thank you, Mr. Chairman, for holding the hearing.
Would you like an answer?
Yes,
It's
sir.
profoundly dishonest. And I think integrity is important. I think Mr. Baird emphasized that. If somebody is asking you how climate changed, and you influence your answer because you have some ideas on energy policy, you are shortchanging your interlocutor. And I don't think that's appropriate. If somebody has an energy policy they wish to propose, it should be defended on its own grounds and sold on its own grounds. The notion that a climate scientist who disagrees that CO2 is important there should join the bandwagon, or even if they did agree, to push my view of greenhouse gases, I'll also support your view of energy. It's confusing the issue for the public. It's not helping it for everyone to march in lockstep.
Sir, in a former life, I was a scientist. I have a PhD. I have about 100 papers in the literature. I understand science, and I'm a rare Republican. I tell audiences that I'm a conservative Republican, but on these kinds of issues, I'm not an idiot.
Well,
and
I'm not accusing you of that, but I am saying that when you ask a scientist to lock arms with a politician because they both have aims that have the same policy, that's probably dangerous.
Oh, if the goal you want to accomplish is a national security goal, and ultimately it is, then I don't see a compromise of science, because you happen to have a common goal with a political or a military person.
Dr. Bartlett, if I may, as well as I know Dr. Bartlett, I would never expect Dr. Bartlett to suggest that a scientist should modify his or her findings to fit a political agenda. And this, by the way, goes both sides. But I do believe what he's suggesting, and he suggested it many times, and not only does he suggest it on the hearing, he embodies it in his life, that there are national interests that are meritorious beyond, the debate today is about the scientific findings, but I think what he's saying and what he's literally embodied in his own life, he's more off the grid than anybody I know. I mean that as a compliment. Off the electricity grid, because he's so on the grid of the data. He's saying, I think, that this is not a matter of distorting the scientific findings, but let's make our policy consistent with a common interest.
Yes, sir. We have three common interests, and there is no reason that we should be limiting our ability to reach those common goals because we simply disagree with each other's premise. That's all I'm saying.
Dr. Cicerone, I know you want to comment, but I'm going to invite Mr. Rohrabacher to rejoin us. If we have time, I'll get back to you on this matter because I know it's important. Mr. Rohrabacher.
Thank you very much, Mr. Chairman, and again, we will miss Chairman Baird, and I appreciated his leadership, although we have strongly disagreed on several issues, this being one of them. And I actually would thank him very much for including one witness out of four to present the other's point of view. The fact is, in the past, as the chairman or as Ranking Member Hall mentioned, we've had one witness in a whole hearing as compared to any type of balanced presentation. This has been this tactic of not permitting the other side to be heard or trying to muzzle people in academia and elsewhere from expressing opposition views to the man-made global warming theory is a travesty. And it's about time the people in the scientific world admit that that's what's been going on. Because what we've had is Yeah, one witness out of 4. In the past, we've had one witness out of 16. And how many of us have heard over and over again, case closed, where there are presentations with nobody on the other side being able to express their opinion? They made a mockery out of science, and I'm very happy that at least today we have one witness out of 4 in the panels who are going to present the other side. Because there is a fundamental disagreement on whether or not the climate cycle that we are in today is basically being caused by mankind, or whether or not this is a natural cycle. And if it is created by some sort of human activity, is it something that we should be concerned about because it is not a major factor, but a minor factor in what's going on? Mr. Chairman, I noted that you used your case to say why CO2 should be more concern in terms of because it does than oxygen in the atmosphere, because CO2 does absorb more heat. Well, let us just note that oxygen is, I believe, 21% of the atmosphere. CO2 is 390 parts per million. That's one half, less than one half of 1/10 of 1% of the atmosphere, as compared to 21%. Of this, 58 parts per million are man-made, as compared to what's in there naturally. So this idea that CO2, most of the people who are discussing this issue, that the presentation to the public has been so skewed, and the debate has been so hampered by not presenting the other side, that most people believe that CO2 represents 10% or 20% of the atmosphere. Ask the people around you, and you will find even members of Congress giving you that answer. Well, today we are trying to get to the bottom of this, and I appreciate the fact that, again, we have a debate where at least 1 out of 4 witnesses is going to be able to address some issues. Let me ask Dr. Lindzen. We have some of the points that you've made, but I'd like to specifically ask you whether or not you believe that there will be dire consequences due to our lifestyle on the climate of this planet.
No, I don't think so. I think we're talking about finite issues. The elevation of finite issues to catastrophism probably would leave behind a large portion of the scientific community. I think there's been a problem that the agreement is on the trivial. The controversy is on really obscure things that depend on many factors. I mean, one of the things that bothers me in the discussion of extremes and storms and so on, a basic feature of meteorology is the cause of storms in mid-latitudes is the temperature difference between the equator and pole. Under a warmer climate, that should be reduced, and that should lead to fewer storms. It is the storms that bring in record highs and lows by carrying air from distant places. Why suddenly in this complex thing a particular observation that is actually contrary to the basic physics assumes importance, I don't know.
Well, we have had many cycles of warming and cooling throughout the history of this planet. Of course. Many cycles. And a minuscule change in the amount of CO2 in the atmosphere as compared to other time periods when there were other cycles going on, when CO2, by the way, was dramatically higher than what it is today. We have seen that this is the relationship between CO2. This is what it comes down to. People are trying to tell us, in the scientific community, there are people trying to tell us that we have got to accept draconian changes in our way of life, mandated by law, because the CO2 that we are emitting is going to cause drastic consequences to the planet's climate. That does not seem to hold up by even
It's also that even if the U.S. shut down, period, retired from the world, its impact on the CO2 levels would be rather undramatic.
and the CO2 levels in the atmosphere are rather undramatic.
Yeah.
The fact that CO2 is a minor, minuscule part of the atmosphere. It's increased during the time period where mankind has increased the standard of living of the people of the human race, has been used as a scare tactic to frighten people into accepting controls over their lives that they otherwise would not accept. That's what this debate is all about. And frankly, I've seen in the past, I'm a former journalist, I've seen example after example where people in the political world will try to frighten the public on an issue in order to achieve a political end. And this is one of the worst examples of that I've seen. Thank you very much, Mr. Chairman.
Mr. Rohrabacher, whereas you began your statements by emphasizing the importance of hearing from all sides, and during the most recent questioning you heard from one side, I'm going to invite the witnesses, other witnesses, if they wish to respond to some of the points you made, to do so, because I'm sure you'd want to hear their response.
Go ahead. No, you go ahead.
Yeah, there was a number of different points made there. I don't quite know where to start, and maybe I'll just take a couple of them. I think this is one of the things that I personally find difficult, is a lot of times the science gets kind of blurred together with the political side of this issue. What we're here to talk about is the science of this issue. When you talk about dire consequences, those are value judgments made by human societies that those aren't science issues. So, there's been an effort in the European community to come up with a number of 2 degrees C warming above pre-industrial as a threshold for dangerous climate change. And people argue about that a lot. And that number is out there, but I think you'd find a lot of disagreement even among the scientific community about what constitutes dangerous climate change. Certainly, with climate change, things will shift around. You'll have dry areas probably getting drier, wet areas will get wetter. You'll see changes to extremes. You see things that would have impacts on human societies. But the fact that these greenhouse gases, which we call trace gases because, as you point out, rightfully so, they constitute a really small fraction of the composition of the Earth's atmosphere. The fact that they have this interesting and unique property that they have more than 2 atoms per molecule. Oxygen, nitrogen, which are the biggest constituents, as you say, have only 2 atoms per molecule. When you have more than 2 atoms per molecule, that makes that molecule really active and really important, and it can absorb and re-emit heat and trap it. So I think that...
But if it's so minuscule, how does that then have a greater impact?
Yeah, see, that's the interesting thing about it, because even with these really small quantities, they can be really important to the climate system and really make a difference in how the climate of the Earth is behaving. So I think it's in terms of the science, these are the things that we grapple with too. We try to incorporate these things in the models the best we can, and we're trying to use the tools the best we can, and these are the indications that we get. In terms of evidence, science is a great thing because, Dick has theories about, low climate sensitivity. Other people have tried to use other evidence to contradict what he said. And this is how science works. We have this ongoing discussion, and we kind of try, in the end of the day, try to come up with some idea of what we think is really going on out there in the world. So I think that's why all of us probably got into science in the first place, because we're really interested in how the world works. But focusing on the science makes it a very interesting problem that has all these interesting things that go on in terms of physical processes that we can try to use tools like climate models to understand. And I think that's where the interest is for us, and I think that's what makes this a very interesting problem. Now, as far as what you decide to do as policymakers about this problem is something we can try to give you information. I think Mr. Inglis' example of the advice you get from doctors that, maybe a certain 98 give you, say, A and 2 say B, and you say, well, okay, well, what do you want to do? It's still a call that you have to make as policymakers as to what you do with this information, but I think we have to do the best we can to give you the best possible information from our community.
So help us understand. First of all, I very much appreciate what you said, Dr. Meehl, because on this committee and elsewhere in the public and in the media, there's an assertion that that climate science is a hoax, meaning something intentionally perpetrated. Piltdown Man is a hoax, but I don't see this as a hoax. People may disagree on the findings and their implications in the models, etc. But the idea that it's a conspiracy to force draconian changes or it's a hoax flies in the face of what I know about the individuals on all sides before us today. And so if nothing else, let us put to rest this assertion that in some way you are motivated by some bizarre intent to change our way of life. Help us understand, though, the fundamental question that Mr. Rohrabacher asked about how is a relatively small trace element impact raising temperature. That's really a fun.
As compared to the natural cycles.
That's a fair question.
Because,
Help us understand it.
Yeah.
Dr. Cicerone, I'm going to call him. We'll
I'll
work
be
our way
happy
down.
to answer that. There is no simple relation between the amount of a constituent and its ability to absorb radiation. If you have a very strong absorbing molecule, then you need less of it to do something. CO2 is a significant absorber. I differ with my colleagues about the reason why. It's the permanent dipole moment that's important. And, OH, NO all have two atoms and they absorb well in the infrared. So I don't know, that makes me wonder about the testimony, but still, it is possible for a trace gas to be important. It isn't strictly the amount, even though the amount is minuscule. For instance, a very thin, visibly invisible cloud will absorb more infrared than all the other infrared absorbers in the atmosphere when it's present.
Dr. Cicerone?
The framework is the energy balance of the planet. And so in deciding whether an entry is small or diminutive or whatever, it's when we look at those balancing, as you said, Mr. Rohrabacher, that compared to the natural balances. And these polyatomic molecules that have vibrational and rotational modes that they can interact with the infrared radiation, as Dr. Lindzen just said, sometimes the tiniest presence can intercept parts of the spectrum which are otherwise transparent. Generally speaking, the Earth's atmosphere is transparent in some of these infrared wavelength regions where the planet's emitting. So it's not too much of a mystery. We have to go through the numbers. If I may, Mr. Chairman, could I make a comment on Mr. Bartlett's very interesting puzzle about energy policy?
Please, and then I'll give one more opportunity to others, and we'll finish. We have two more panels to get, so I want to make sure.
I've heard a very graphic presentation of the same three conundrums in testimony to the House from a former CIA director, Jim Woolsey, where he gets back to your three overlapping groups and interests by having a fictional conversation between John Muir, Mahatma Gandhi, and General George Patton. And he shows that they can agree on the kinds of things that you just said. He testified in the House a year or two ago, and I've heard him give this presentation. It's fascinating. Getting down to basics, energy efficiency is a solution that should appeal to all three of your groups, and yet if all of this free money is lying on the floor to be saved with energy efficiency, why aren't more people taking advantage of it? We now have some analysis from business groups of why various companies and individuals are not doing more to capture this free energy through efficiency. And I'm optimistic that people will get their acts together who are concerned about those three different sides of the issue.
Any final comments from Dr. Meehl or Dr. Cullen, and then we'll release this excellent panel for the next one. So.
I think one remark I'd like to simply make is that with this notion that extreme weather events will increase over time, I think it's important to just remember in our daily lives as we move forward, there's numerous things that we all need to worry about. And if you look at the tragic events that happened during the Nashville floods, yes, we've dealt with extreme weather events in the past, but from an infrastructure standpoint, from doing things in the short term to reduce our overall vulnerability, I think rather than think about catastrophism, it's thinking about the fact that we have information that can reduce our overall vulnerability, make our communities stronger. And, I just come back to the fact that just as meteorologists on the short term are trying to keep people out of harm's way, this is information that is ultimately meant to make our communities stronger and safer. And it's sort of as simple as that as we move forward over the next decade or two.
Dr. Meehl, any final comment? I want to thank this outstanding panel for their expertise, for their years of work, and for modeling a productive and constructive discussion. Thank you very much. We'll recess for about 4 or 5 minutes till the next panel can be seated. And I'm sure my colleagues join me in thanking this panel of witnesses, and I'll ask them to retire at this moment, and we'll invite our others to join.
Somebody tells them a woman is giving birth to a child.
I appreciate everyone joining us again. We now will begin our second panel. And as before, it's my pleasure to introduce our second panel of witnesses. Dr. Patrick Michaels is a senior fellow at the Environmental Studies for the Cato Institute. Dr. Benjamin D. Santer is an atmospheric scientist for the Program for Climate Model Diagnosis and Intercomparison at Lawrence Livermore National Laboratory. Dr. Richard B. Alley is the Evan Pugh Professor for the Department of Geosciences and Earth and the Environmental Systems Institute at Pennsylvania State University. And Dr. Richard Feely from my home state of Washington is a senior scientist for the Pacific Marine Environmental Laboratory with the National Oceanic and Atmospheric Administration. As our witnesses observed before, we'll do our level best to try to stick to 5 minutes. Sometimes if you go over a little bit over, I'll be as patient as I can. But please do your best to keep it 5 minutes, and following the presentations, we'll have a series of questions. Again, I thank our witnesses. Dr. Michaels, you're welcome to begin. Thank you.
Thank you, Congressman Baird. It's very nice to be here. It's an honor to be here. I think the first panel set what I think is an interesting scientific discussion. What we're really looking at here is to whether the sensitivity of temperature to carbon dioxide is as large as some people think, or whether there are other factors that are responsible for the temperature changes that we have seen. And I'd like to show the first slide, if I could. The important thing about climate change to remember is that it doesn't matter whether people change the climate. One of the rhetorical devices that is inaccurate on this is to say all scientists agree that human beings have an influence on climate. So what? What matters is how much we influence the climate, and we are getting some guidance from Mother Nature on this, despite our best efforts, if you will. This slide shows each piece of colored spaghetti on this slide is a computer model. There are 21 different models from the United Nations IPCC scenario for concentrations in the atmosphere that pretty much resemble what's been going on in the atmosphere. One of the things you see is each one of those pieces of colored spaghetti is pretty much a straight line. And the reason for that is because we put carbon dioxide in the atmosphere exponentially, but the response is logarithmic, and it tends to do that. Now, ask yourself the question, since the planet started its warming of the late 20th century, has the warming been a straight line? And the answer is yes. So how do you discriminate between these straight lines? The same thing you tell students in weather forecasting, which I've taught. When different models say different things, look out the window. And when you look out the window, what you see here is it at the low end of this line. Now, I hope it went to the next image. Very, very good. Another way to look at this issue is to look at the frequency distribution of temperatures produced by all these temperature trends produced by all these models for periods, say, of 5 on out to 15 years. And the blue line are the observed trends from the Climate Research Center at the University Climate Research Unit at East Anglia. And what you can see, which corresponds to what we saw on the last slide, is in fact the warming is clearly below the average predicted by these models. Yes, we have a greenhouse fingerprint, and we're going to hear about that in this talk. But I submit to you that it's a pinky. It's not one of the dreaded other fingers. And furthermore, if we take a look at the attempts like this, they are very sensitive to the years that are chosen. This particular paper right here is probably the most famous paper ever published on attribution of climate change. It appeared in 1996, and it shows that the temperature between 1963 of the free atmosphere and 1987 corresponded remarkably to what was modeled. It was fantastic. It was a wonderful result. And here is the left-hand side is the computer. You can see in the southern hemisphere, which is on the right-hand side of the left-hand image, a massive warming. And you see from 1963 through 1987 in the southern hemisphere, a massive warming. What a wonderful finding. But the weather data actually begins in 1957, the weather balloon record for this, and ends in 1995 for the purposes of a paper published in 1996. I offer you the observation, by the way. This paper appeared 4 days before probably the most important conference on climate change ever held by the United Nations Policy Committee, and it was highly, highly influential. At any rate, when you add in all the data from 1957 through 1995, the relationship vanishes. So these studies are very, very sensitive to what goes on with the temperature, what period we study, rather. So the search goes on. Sulfates, aerosols, the sensitivity or the effect of them is estimated between 0 and -2 watts per meter squared. You can pick pretty much any value you want, which makes it very easy to fit curves. And then there's the problem of volcanoes. After this appeared, another research effort was made to look at the effect of volcanoes on the temperature. You see, scientists actually are involved mainly in trying to find out why it has warmed so little compared to the greenhouse gas only models. And so it was a paper came out by pretty much the same group that said, well, if we go back to Krakatoa in 1883 and we factor in the volcanoes, my God, 2/3 of the warming that would have occurred has been suppressed. Wow, that's another remarkable finding that turns out to be incredibly time dependent, because you see, there were volcanoes before 1883. Mount Tambora went off in 1815, created the year without a summer, 1816. We have these records. And very recently, Jonathan Gregory just got a paper accepted, and it will be published very soon, which uses the entire volcanic record. And I offer you, this is an artifact of experimental design caused by the models having been spun up to a steady state with episodic volcanic forcing before the historical simulations began. This artifact could be misleading in comparisons and attribution observed in simulated changes in climate. So I'll tell you what my conclusion is. First of all, scientists work by tentative hypotheses. And you look at data to see whether you can maintain your tentative hypothesis or whether you have to modify it. My tentative hypothesis would be that the sensitivity has been overestimated in agreement with Lindzen and Spencer and a whole host of other scientists. And that is the prospect that we need to test. Now, I realize some people might not agree with me on this, because some people say there's no such thing as climate change, and some people say, well, yes, climate change is the end of the world. If you disagree, you can join this Facebook site that appeared, and you can take care of me. Thank you very much.
Dr. Santer.
Thank you very much, Chairman Baird, for the opportunity to talk to you here today about climate change and have a rational discussion. I'm not going to address some of the issues that Professor Michael raised. I hope that I may be able to do so in the question and answer session. Today is November the 17th, and my dad was born 91 years ago on November the 17th, 1991. This figure is from the report which was published last year of the U.S. Global Change Program, Global Climate Change Impacts in the United States. And what you see on the right-hand side is a scale that shows you the change in atmospheric CO2 levels, as Dr. Cicerone mentioned earlier, measured worldwide. On the left-hand side, the temperature change, this difficult estimate of the average temperature of the planet. And the point I want to illustrate with this, that over a human lifetime, there has been a change from roughly 300 parts per million per volume CO2 in the atmosphere to 390. That's not a belief system. People often ask me, Dr. Santer, do you believe in global warming? I believe in facts and evidence. This is a fact. I think we can all agree on this. So the question is, what did this change in atmospheric composition do, if anything? Well, that's a difficult question to answer. Climate change is not an either-or proposition. It's not either all human influences or all natural influences. Clearly, many things are happening simultaneously. Massive volcanic eruptions, changes in the sun's energy output, human changes in greenhouse gases and aerosol particles. The difficulty is separating the natural factors from the non-natural factors. In the real world, of course, we can't do that. We have no undisturbed Earth without any human intervention. But with computer models of the climate system, we can look purely at the natural factors, and that's what you see here, and how they may have changed over the 20th century, changes in the sun's energy output and volcanic aerosols. You use a computer model, many computer models in this case, and what you can see is that just with natural factors, you can't explain the warming we've observed over the second half of the 20th century. When you put in combined human and natural factors, you can. Now, this isn't convincing evidence. I agree with Dr. Lindzen on that point. He said, if you just look at global temperature alone, it's difficult to make reliable influences about causation. And that's why, as scientists, since 1979, since the first paper on fingerprinting, we've looked beyond the global mean. We've looked at complex patterns of climate change. And what you see here, again from last year's Global Climate Change Impacts in the United States report, is a model-based estimate of the fingerprints of different factors which affect climate. And there are 5 different fingerprints up there. There are changes in well-mixed greenhouse gases. There are changes in sulfate aerosol particles. Both of those are human. Sulfate aerosols are produced by the burning of fossil fuels. Then there are changes in stratospheric and tropospheric ozone, changes in volcanic aerosols, solar irradiance, and then the final pattern is all factors considered together. Now, I don't want to go into the details. The key point here is that they're all different, and what we're doing here is we're looking at slices of the atmosphere from the Earth's surface right up to 20 miles and from the North Pole to the South Pole, and these are model-based estimates of changes in temperature over the last 50 years of the 20th century. They're different, and we exploit those differences in fingerprinting to try and understand cause and effect relationships. As you've heard, some people still posit, even today, that the sun explains everything. That is a testable hypothesis. We routinely look at that hypothesis. Our best understanding is if the sun's energy output had slightly increased over the last 50 years, there would be more solar energy arriving at the top of the atmosphere. We would see heating throughout the full vertical extent of the atmosphere. We don't see that. The reality is that the observations look much more similar to the top fingerprint, the signature of well-mixed greenhouse gases. They don't look anything like the sun explains everything. Also, as Dr. Cicerone mentioned earlier, for the last 30 years, we've measured in a number of different satellite instruments the sun's energy output in space, and we know that there are these 11-year cycles, but there's no overall increase in temperature over the in solar irradiance over the last 30 years. There is, however, an increase in temperature over the last 30 years. So the sun explains everything does not convincingly explain observed climate change. Doesn't fit the bill. Now, back at the time when this fingerprinting work first came to the fore, Professor Michaels mentioned that in the mid-1990s, it was criticized, quite rightly, I believe. People said if there really is a human-caused fingerprint in observations, go look in it, go look in many different locations, not just at the surface of the Earth, not just in atmospheric temperatures, but look in rainfall, look in moisture, look in pressure patterns, and that's exactly what the community has done. The community has looked in many different aspects of the climate system, used these statistical rigorous comparisons to look at patterns of change, not global mean numbers, and has been able to show that the changes in all of these things are not consistent with natural causation alone. Now, you may not like that result, but that's our best understanding that we have. The climate system is telling us an internally and physically consistent story.
Thank you, Dr. Santer. Dr. Alley.
Yes, thank you for the honor, Chairman Baird, Mr. Urbacher. It's a pleasure to be here. Your body has, in its wisdom, established mechanisms to gain assessment of the science, because as you know, we scientists sometimes can argue about things. In fact, you pay us to argue about things. We love arguing about things. And so you have set up things such as the National Academy to give you assessments that are outside of the argument, say, what does the science say? And if you look at the assessments, the science is now very clear. For my interests are especially with ice as well as climate history, and the science says that the ice is melting almost everywhere, almost all of it, consistent with warming. There's a few really cold places, the top of Greenland and the frozen ocean water around Antarctica, that increasing precipitation has still been controlling, and that's also consistent with our understanding of the effects of warming, and that is projected to switch to shrinkage in the fairly near future. So when we look at the world, what we see is ice shrinking because it's getting warmer, and in fact you can estimate the warming from looking at how much the ice shrinks, and that agrees with the thermometers. This is the plot of melting of mountain glaciers contributing to global sea level rise. You will find people that put the plummeting one there and say catastrophe, and you will find people that look at that blue one on top that's Norway that grew a little bit before it started shrinking, or they look at one wiggle in that black one, which is the Himalaya, and they say, oh, nothing's happening. If you look at those curves, the mountain glaciers assessed, taken together, are shrinking, and they're contributing to sea level rise. And there's really no serious question about that. Now, if we want to know what happens in the future, this is a very complicated plot, and I hope that you don't look in any great detail at it. This is how much warming we expect from rising CO2. And this particular one is if you just doubled CO2, and then let the climate come into equilibrium, how much warming. We may go way past doubled CO2, but the blue number up there, which is a little over 5 degrees Fahrenheit, is sort of the most likely. If you could bet on one horse, you'd bet on that horse. You've heard Dr. Michaels, and earlier you heard Dr. Lindzen arguing, well, couldn't it be lower than that down the green arrow? And it certainly could be. That's within the realm of scientific possibility. But the orange arrow shows that it could be higher than that, and the red arrow shows it could be a lot higher than that. You have now sort of had a discussion or a debate here between people who are giving you the blue one and people giving you the green one. This is certainly not both sides, if you want both sides. We'd have to have somebody in here who is screaming Harry Panic conniption fit on the red end, because you're hearing one very optimistic side. We wish that Dr. Michaels and Dr. Lindzen were correct against the assessed central value. Now, when we look at the impacts of warming, we get the same sort of story. The IPCC looked at sea level rise, and they said, well, this century it's probably not going to be huge, but that excludes anything weird that the ice sheets do, and we're very nervous because the ice sheets have started doing something weird, and they started doing it 100 years before we expected them to from the previous assessment. So when you look at sea level rise, what you find is that it's going to rise. There's virtually no way to avoid that. But there's a big unknown. And so if you look at what people have been planning for, it's something. It might be a little better, a little worse, or a lot worse. But we don't find any evidence for a lot better. The ice sheets are already shrinking, and they're shrinking way before we expected them to. Now, we do not believe in any way that you could melt a whole ice sheet in mere decades. But we are very nervous that within decades we could get warm enough to melt a whole ice sheet. Now, Greenland would be 7 meters plus of sea level. Antarctica is very much bigger than Greenland. The last estimate I saw, 10% of the world population lives within 10 meters of sea level. And so the amount of ice which is in play is huge for people and where they live and what they do. We don't have really reliable projections, but we do see sea level rising and the possibility that this century we get to a point where we're committed to very, very large rises. So the planning people have been doing is, this is our best estimate. It could be a little better, a little worse, or a lot worse. Where worse, I mean larger impacts on people. So just to summarize then, it's getting warmer. That's melting ice. This is all consistent with what we understand about what should happen. Everything is in there. We keep hoping that we've overestimated the impacts. It'll be better than that. But if you plot all of the unknowns, it could be a little better, a little worse, or a lot worse. Thank you, sir.
Dr. Feely.
Good morning, Chairman Baird, Ranking Member Inglis, and members of the Subcommittee. Thank you for giving me the opportunity to speak today about ocean acidification, its impacts on marine life, and our economic values. I know this issue is one that this subcommittee has strongest interest in, and I'd like to recognize and thank your bipartisan leadership in passing the seminal legislation, the Federal Ocean Acidification Research and Monitoring Act of 2009, is now driving the force behind a NOAA interagency and academic effort throughout this country to understand this new phenomenon. Fundamental changes in seawater chemistry are occurring throughout the world's oceans. Over the past 2.5 centuries, the release of carbon dioxide from the industrial agricultural activities has resulted in atmospheric carbon dioxide concentrations that have increased from 280 to about 390 parts per million. To date, the oceans have absorbed about 1/3 of the carbon dioxide emissions by human activities during this period. This natural process of absorption has benefited humankind by significantly reducing global warming in the atmosphere and reducing some of the impacts of global warming as well. However, decades of ocean observation and research from NOAA, the National Science Foundation, and Department of Energy has shown that the daily uptake of 22 million tons of carbon dioxide is having a significant effect on the ocean's chemistry and biology. When carbon dioxide reacts with seawater, chemical changes occurs that cause a decrease in seawater pH and carbonate ions. These chemical changes are largely referred to as ocean acidification because of the direction of change involved. Scientists have estimated that ocean pH has fallen about 0.1 pH units since the beginning of the industrial period. This first slide I show you shows the atmospheric concentration of CO2 at the Mauna Loa site that Dr. Charles Keeling started in 1957 in red. And underneath it in blue, you find the Hawaiian Ocean Time Series site that's maintained by the University of Hawaii under the direction of the National Science Foundation. And you can see the increase in surface ocean PCO2 is commensurate in the terms of the rate of change with the atmospheric concentration, about 1.5 parts per million per year. And underneath that is the corresponding pH measurements from this site. And we see a 0.02 pH change at this site over the last decade. So you can see from measurements alone, we can see the acidification process. Since the pH scale is like the Richter scale, is logarithmic, this change in pH represents a 20% increase in the hydrogen ion concentration of seawater, or the acidity of seawater. Further predictions out to the end of the century suggest that we could have a 150% increase in the acidity of seawater using the IPCC business as usual scenario. Now, it's important to note that right at present, we are exceeding the CO2 emission scenarios to date. Many marine organisms that produce calcium carbonate shells and skeletons are negatively impacted by increasing ocean acidification and been shown to reduce their ability to produce their shells and skeletons. For example, in a recent paper just published last week, the coral reef biologists have shown that acidification could compromise fertilization and settlement of elkhorn coral. Elkhorn coral is an endangered species, and we are causing further harm to that. These research results suggest that ocean acidification could severely impact the ability of coral reefs to recover from any kind of disturbances, including major storms. Other research indicates that by end of the century, coral reefs may erode faster than they can be rebuilt. This could compromise the long-term viability of those particular ecosystems that perhaps impact over 1 million species that depend on coral reefs for their survival. Ongoing research that decrease in pH may also negatively affect commercially important fish and shellfish species is well underway. Both crab and sea beam larvae exhibit high mortality rates in a high CO2 world. The calcification rates of edible mussels and Pacific oysters declined linearly with increasing CO2 levels. Since 2006, some oyster hatcheries in the Pacific Northwest along Washington, Oregon, and California have experienced massive mortalities of oyster larvae in association with a combination of factors, including the upwelling of cold, high CO2-rich waters. Scientists have also seen a reduced ability of some types of marine plankton that produce calcium carbonate shells. And these organisms are food sources for many marine species. One type of free-swimming mollusk called a pteropod is eaten by organisms ranging in size from all the way from krill to whales. Pteropods are the major food source for North Pacific salmon and are major food for mackerel, herring, and cod. You can see the importance of these species to our ocean ecosystem as they ride through the food chain. The impact of ocean acidification on our fisheries and coral reef ecosystem could reverberate through the U.S. and global economy. The U.S. is the third largest seafood consumer in the world, and total consumer spending on fish and shellfish of about $70 billion per year. Coastal and marine commercial fisheries generate up to $35 billion per year and employs 70,000 people. Ocean acidification is caused by the buildup of carbon dioxide in the atmosphere and can have significant impacts on marine ecosystems. Ocean acidification is an emerging scientific issue, and much research is needed before all the ecosystem responses are understood. However, to the limit of the scientific understanding we have about this issue right now, the potential for environmental, economic, and societal risks are very high, hence demanding serious and immediate attention. Thank you for your attention, and I look forward to your questions.
Thank you, Dr. Fitty. Thanks to all the witnesses. At this point, I'll recognize myself for 5 minutes, and we'll follow with questions from my colleagues. Dr. Fitty, you focused on the evidence of ocean acidification. It appears a pretty strong connection. Two questions for you. One tangential. There's, my understanding, been an enormous coral die-off worldwide, particularly in the Caribbean, as we've seen coral bleaching from high sea temperatures. Can you very briefly comment on that? And then secondly, are there alternative explanations that seem credible to explain the acidification levels that you've been measuring?
To answer your first question, because of the increasing level of temperatures in the ocean, we have seen coral dive-offs as much as 16% globally, and the projections are that out to the end of the century, we may not see very many of the coral reefs be able to survive. That's the dire situation we're faced with. The concern that we have in terms of acidification is that some of the preliminary research has shown that the combination of increased CO2 and the increased temperature associated with global warming enhances the bleaching impact on those corals. So their risk of survival is even greater.
Do you want to? Are there other alternatives? What would somebody would say? What's another alternative explanation for the measured increase in acidity, or in other words, lowered pH, other than the CO2 hypothesis?
The major suggestion is that perhaps CO2 evolution from volcanic activity, hydrothermal activity in the deep sea, could be enriching the CO2 levels in the surface oceans. We have published papers on this subject to show that the amount of CO2 from volcanic activity in any given year is 1/100th of the amount of CO2 that enters the atmosphere through man-made activities.
Thanks, Dr. Feely. Dr. Alley, two questions. One, tell us a little bit about how, from your graph, it looked like you feel pretty confident that the data suggests ice sheets and glaciers, et cetera, around the world are melting, with a few exceptions. Tell us a little bit about the methodology by which that is measured first. But secondly, haven't there been times in the past when we've seen receding glaciers and receding ice sheets and comments about, my goodness, things seem to go in the opposite direction, glaciers, and what's the difference now?
Right. So for measuring, say, what Greenland is doing, some of that work is done by weighing the ice sheet using the GRACE gravity satellites, which is truly wonderful. It's like watching cars on a roller coaster, and the one going down gets away from the one that's going up, and then the one going down catches up, and you watch.
As I understand, it's fascinating that we've satellites sort of pursuing each other, and gravitational attraction slows one down, and relative to the other, and by measuring the rate of that different speed, you can tell how much mass is underneath you, and as that mass declines, there's less slowing down.
Perfect. I should retire and let you teach this.
I just think it's beautiful. Really interesting.
So you weigh them using GRACE, but then you measure changes in surface elevation. Is it going down or up using a radar or a laser from a plane or a satellite? And all of those have been done. Okay. And then you figure out how much snow is being added and how much meltwater is leaving and how much ice is leaving. And then you compare all of these to see if they give the same answer. And all of them indicate shrinkage of Greenland. You're certainly correct that the ice has grown and shrunk in the past, and I had the honor of serving for the U.S. government on the Climate Change Science Program on a report on the history of the Arctic, and what we found was very clear for Greenland. When nature made it warmer, Greenland got smaller, and when nature made it colder, Greenland got bigger. And we are now making it warmer, and Greenland is getting smaller.
How do we know it's we, not nature? We've got the increase in CO2. But the skeptic would argue, well, wait a second, I can go back to 1927 and find articles about glaciers retreating. What's the difference? I mean, you know, you could look at a football team and say, well, they were losing back then and they're losing now, so what's the difference?
Right. So the first one is the physics. We just cannot get away from the warming effect of CO2. It's been known for over a century. It was really clarified by the Air Force, who were actually interested in what wavelength should I use for the sensor on my heat-seeking missile. But CO2 interacts with radiation, and there's enough CO2 to make a difference. And we just can't get away from that physics. The second one is looking at, is there any other possible thing to explain this? And it really took, I'm sorry, sir, it took a few $1 billion of your money and about 30 years to say that there's nothing else that we can find in nature to do this. And this is because satellites are expensive. But someone says it's the sun. Well, then you need a satellite to watch the sun to see if the sun is getting brighter, but it isn't. And if someone says, well, it's volcanoes, then we need a history of volcanoes, and we need to know what they're doing. And if someone says it's cosmic rays, we need cosmic ray monitors. And it's taken sort of 30 years to get to the point of saying, no, we've looked really hard. We can't find anything else. Then there's a third piece, which is the fingerprinting, which is what Dr. Santer was discussing. If you were to say, okay, yeah, I know we spend a lot of money on satellites, and the satellites say the sun is not getting brighter, but maybe the satellites are wrong, and the sun's getting brighter, and we can't see it. That makes a prediction. It gets warmer down here, and it gets warmer way up at the top of the stratosphere. CO2 says warmer, colder. What's going on? Warmer, colder. So the fingerprinting in time and in space says that we got it right on the other two pieces. It's mostly us now.
I want to be clear, it's not my money. It's your money.
Okay. Thank you, sir. Absolutely.
It's the taxpayers' money. I never
Absolutely.
forget it. But I think at the same time, the consequences adversely, if we don't address our energy dependence, and if we don't address the apparently, in my judgment, real impacts of this, will vastly exceed $1 billion. And if we can make some measured changes to reduce that impact, the savings will exceed the expenditures by a darn sight. Dr. Santer, you might want to comment. Dr. Michaels, then I'll recognize my colleagues.
Yeah, I just wanted to comment briefly on what Dr. Ali said about the fingerprinting. We've known that increases in CO2 have this characteristic fingerprint of warming the lower atmosphere, the troposphere, and cooling the upper atmosphere since about the late 1950s, early 1960s, when people performed the first numerical model experiments and doubled CO2, and they saw this characteristic pattern of cooling of the stratosphere, warming of the troposphere. Very robust. We see that in virtually every model experiment that's been performed. And as mentioned, we also see it in observations too. We see it in satellite data. We see it in weather balloon data. Now, people often say these computer models are not falsifiable. They make predictions that we can't test. That's not true. Back in the 1960s, when Suki Manabe and his colleagues at the Geophysical Fluid Dynamics Lab in Princeton made these calculations and doubled atmospheric CO2 and saw this fingerprint, we didn't really have the observational data to see whether the stratosphere was actually cooling, whether the troposphere was warming. They have. The stratosphere has cooled, the troposphere has warmed. That fingerprint is robust, and it's just not consistent with other natural causes.
Dr. Michaels, did you care to comment on any of this?
I have several comments I'd like to make that would probably take up the rest of the day, so I'll just limit. That won't happen. No, it certainly won't. I will limit it to the notion of what we're talking about here. You've noticed is that everybody says that the planet's warmed up and that people have something to do with it. So what really matters is the magnitude of it. If I can have the clicker. Where's the clicker hiding? This is just going to take a second. It's not going to be as bad as you think. There it is, right there. This is the warming from the IPCC, from the CRU record from 1950. And our Environmental Protection Agency, which, as you know, has taken over the regulatory aspect of this because of what happened in the Congress, issued an endangerment finding on warming. And they asserted in their endangerment finding that more than half of the warming of the late 20th century is a result, very likely, a result of human greenhouse gases. More than half means more than 50%. Late 20th century means after 1950. You agree with that? I said second half of the 20th century. Well, in fact, there are 4 different factors that are totally independent of the greenhouse effect. One, that we underestimated sea surface temperatures from 1944 through 1965. That was published by Thomson in Nature magazine. Number two, that there are non-climatic subtle effects on the temperature history. That was published by McKittrick and me in Journal of Geophysics, Atmospheres. Susan Solomon found that water vapor in the stratosphere is responsible for a lot of the secular changes, and that we don't know why water vapor is fluctuating in the stratosphere. It's not a greenhouse effect. I mean, it's not apparently from greenhouse gas emissions. And number four, Ramanathan at Stanford said, well, about 25% of the warming is the result of black carbon going in the atmosphere. That's also not a greenhouse gas. When you add all those up, the warming drops from 0.7 to 0.3 degrees. So the assertion that over half the warming is a function of greenhouse gases is challenged by four completely independent factors. I think we've got a lot more work to do on this, frankly.
Any very quick response to that, Mr. Inglis?
Yes, might I respond
Please,
to that?
very quickly.
Dr. Michael's analysis is wrong. I'm sorry, it's just completely incorrect. What he's attempted to do here is explain the observed temperature change over the last 60 years, from 1950 through to 2010. And he said that the estimated total change in temperature is 0.7 degrees. Now, he's identified four things: economic activity, black carbon, errors in the sea surface temperature data, and stratospheric water vapor, and said, I think all of those things have had a warming influence, so I'm going to subtract them from this 0.7 degrees, and I'm left with 0.3. 0.3 is less than half of 0.7, therefore the IPCC is wrong. And the conclusion that more than half of the observed warming over the 20th century was due to, very likely due to increases in greenhouse gases, is one of the central conclusions of the IPCC. So if Dr. Michaels is right, that central conclusion is wrong. What Dr. Michaels did not mention, either here or in his written testimony, is the cooling effect of sulfate aerosols, which has already been discussed at this hearing. If you indulge me for a moment, I'm just going to bring up one slide here. Now, our best estimate of that cooling is sorry, this is a slide from a paper published in 2006 by Peter Stott at the Hadley Center. And what you see in the bottom are three different climate models, and it's the estimate of their sulfate cooling caused by the scattering effects of sulfate aerosols over the 20th century. It's negative. Now, if you assume conservatively that that cooling effect over 1950 to 2010, the period Dr. Michaels looked at was, say, minus 0.4 degrees Celsius over that 60-year period, and you assume that Dr. Michaels was completely correct in the estimating the magnitude of the four factors that he removed from the observations, you'd be adding minus 0.4 and plus 0.4. You'd get to 0. So you still need to explain 0.7. You need to get to the observed total temperature change over this 60-year period. What could that be? Could it be the sun? No way. It couldn't be the sun. If solar effects were that large on the 60-year time scale, we'd see a huge 11-year cycle in the temperature data. We don't. Could it be volcanoes? No, it couldn't be volcanoes. Could it be some mode of natural variability, some internal oscillation of the climate system that could generate that 0.7 degree temperature increase? Not plausible. The most plausible explanation is an increase in atmospheric CO2. We know CO2 has changed. Again, that's not some assertion, that's not supposition. We know that. So what the IPCC found here and what they reported on was that actually the change in temperature due to greenhouse gases, which is what you see in red, was larger than the actually observed change in temperature, which is that horizontal black line. So the greenhouse gas signal was offset, that's our best understanding, by the cooling caused by these sulfate aerosols. They scatter incoming sunlight and they also change cloud properties.
Excuse me. Very pardon for a second. The IPCC gives the range of perspective forcing from sulfate aerosol at 0, a range of from 0 to minus 2 watts per meter
That's
squared.
for the indirect effect.
That gives you an incredible wiggle room anytime you want to make an argument, doesn't it now? It's very interesting to look at sulfate aerosol in terms of the history of science. Now, the first book I ever read at the University of Chicago was The Structure of Scientific Revolutions by Thomas Kuhn. I recommend it to everyone. It predicts that when a paradigm experiences anomalous data, that increasingly strange explanations are brought forth. In 1985, Tom Wigley, who was Ben's advisor, recognized in a paper that the greenhouse gas models were producing too much warming and invoked sulfates. And then you could tune models with sulfates and get things to work perfectly well. Well, the fact of the matter is that our understanding of what the radiative effect of these things are is so wide that I can give you virtually any answer. And so I'm just assuming to leave that alone.
Recognize Mr. Inglis.
And I think it's worth following up on that, because, and this is why this hearing is so valuable, because we get to, these are the kind of things that confuse people and confuse the public a great deal. So, Dr. Santer, you want to continue? What's your retort?
Yes, if I could. Dr. Michaels was wrong again. He claimed that the IPCC's published estimate of the radiative effect of sulfate aerosols was 0 to minus 2 watts per square meter. That serves for the indirect effect. That's for the effect of aerosols on clouds, on cloud cover and on cloud brightness, which is very uncertain. The IPCC's estimate of the direct scattering effect of aerosols, how they scatter incoming sunlight back into space, does not intersect with 0. It is negative, and the best estimate is of order minus 0.5 watts per square meter. The cooling effect of sulfate aerosols has been established not only observationally and in models and theoretically in dozens of studies. We can see these things from space. They're not supposition. This is not science fiction. And leaving out this negative forcing in his testimony to you is misleading you. I'm sorry.
Well,
the
problem here is that the error bars around these things are very, very large, and furthermore, there's an issue with the sensitivity. Excuse me. I'd like to finish. This discussion is really about the sensitivity of temperature to various and sundry forcings. And there is quite a discussion as to, in fact, what the change in temperature is per change in watt per meter squared downwelling flux. If it's on the order of, I think, what Lindzen thinks it is, then the sulfates aren't going to be all that important. So this is an open matter for discussion. I'm sorry, we just don't know everything.
Dr. Santer.
Might I respond very quickly? I'm glad that Dr. Michaels raised the issue of uncertainties. In the fingerprinting work that we do, we constantly look at uncertainties. They're part and parcel of our lives. We look at uncertainties in the fingerprints, those patterns I showed you that arise from use of different models. We look at uncertainties in model estimates of natural climate noise, and we look at uncertainties in the statistical methods that we use to compare models and observations. We spend all our time looking at uncertainties. In this analysis here, you'll see there are no error bars. In this subtraction exercise, no error bars, and the temperature changes are given to within 1,000th of a degree C. Now, to me, again, that is just completely ignoring the significant scientific uncertainties in this partitioning of natural and human effects. You have to account for them. You have to look at all effects, both positive and negative. You can't forget sulfate aerosols. This analysis has not done that, and anything that claims to overturn the central finding of the IPCC's fourth assessment report should do it as thoroughly and comprehensively as possible. This analysis fails in that regard.
Is that why one would use 1963 through 1987 when there was data through 1995? Is that why one would, in fact, begin a volcanic analysis in 1883 when the atmosphere was loaded with volcanic junk? Prior to that?
I'm going to intervene just a little bit. I think for understandable reasons, people have published different papers, and the challenge is if two individuals are sort of in the scientific community going at it with each other, it's an interesting and important discussion, but so I want Dr. Santer to respond to that because you addressed it earlier, Ms. Michaels, but I don't want to dominate it. I'm interrupting my colleague's time here, but I just want to set a little bit of ground. We won't go on forever with this particular debate. So is that all right with you, Bob? If we have addressed, and I'll give my colleague more time to.
Thank you, Chairman Baird. I really appreciate the opportunity to go on the record on this issue. I thank Pat Michaels for referring to this as the most famous paper ever published in climate science. And he criticized this analysis back in 1996 when it was published. I'd like to address three aspects of that criticism very briefly. The first aspect was that the editorial process of Nature had been interfered with, that somehow I had imposed on Nature to publish this paper shortly before the conference of the parties. That's wrong. That's incorrect. The second claim is that there was selective data analysis, that we looked at a time period from 1963 to roughly 1988 in observational weather balloon data, compared computer model output with that, and that if you looked at a longer period of record, you got different results. First of all, Professor Michaels was right. If you looked at a longer period of record, you did get different results. Had there been intent to fool people, to manipulate data? No. We used, since we were doing a fingerprint analysis, pattern observational data, gridded data, and at that time, they were only available from one source. That source extended from 1973 through to 1988. When Professor Michaels criticized our paper, we responded as scientists do. We addressed the scientific criticism. What we found was that when we looked at a newly available weather balloon data set that went through to 1995, he was right, and this change in the temperature asymmetry between the northern hemisphere and southern hemisphere had this sort of U shape. What we were able to show, and what others have convincingly repeated since then, is that that change is forced behavior. If you look at models with combined changes in greenhouse gases and sulfate aerosols, indeed the Stott paper that I mentioned earlier shows that models, when including greenhouse gases and aerosol changes, replicate that behavior. It was not, as Professor Michaels mentioned, some representation of natural causes alone. Actually doing the additional science strengthened our confidence in the ability of the models to reproduce this subtle interhemispheric temperature change difference. Yeah. He has not reported, unfortunately, on those responses to his scientific criticism, which I do not think is correct.
Well, you didn't give Dave Legates the data. Can I ask one thing?
I'm going to recognize
Ask me questions after the hearing. Okay. On this, written questions.
Okay, good. Here, I think it's very interesting kind of back and forth, because it does show that scientists are involved in trying to criticize each other's work in a hope to reach better science, which is very helpful. Then there's some things that are sort of basic. And so, I'm not a scientist, but I play one on science committee when I'm here. So we did this little science experiment that I hope to convince some folks about ocean acidification. What it is an egg that we put in vinegar water. And you come back in a couple of days, and this is a science experiment you did in 7th grade. There's no more shell. Now, this gets rather of worldly concern, because rather than otherworldly and perhaps academic debate, in that, my brother is a shrimper if he had his choice in what he'd like to do. He's got to do other things because you really can't make a living in South Carolina shrimping. And so he's got a pickup truck, and the back of it says, "No wetlands, no seafood." Richard is no tree-hugging environmentalist, but he is a guy who loves to go shrimping. And he knows that if you don't have wetlands, you don't have any seafood. And he's, I think, beginning to see that if you melt the shells of these calcium-based plankton, you end up with a hole in the bottom of the food chain. Now, it is a little bit of a problem to have a hole in the top of the food chain. You lose a polar bear, it's a really bad day. But you open a hole in the bottom of the food chain, Dr. Feely, I think is what you're talking about. You have really ruined a lot of people's day. because, as I understand it, there's something like 1 billion people around the world that depend on the ocean for food, right? Or something like that.
It's about 20% of the protein resources that we as humans require come from the oceans.
Yeah, and so why don't you speak to the, am I right about this, that this is sort of a 7th grade science explanation of how it might work and the risk that we face in the real world consequences of Richard Inglis, the shrimper off of Hilton Head?
Well, if we start at the marine plankton level, which is the marine plants, about 11% of the abundance of marine plants form calcium carbonate shells. These are called coccolithophores. And they clearly show that the formation of the shell is decreased in a higher CO2 world of anywhere from 9 to 45%. And then we go up at the next level. The coccolithophores are generally eaten by the zooplankton. And the zooplankton, such as protozoans, such as foraminifera, for example, or the pteropods that I talked about, these free-swimming pteropods, you can see them with your naked eye. Usually they're about this big, but some of them are about this big. That's the primary food source for juvenile fish. That's what they want to eat, because they don't want to eat plankton per se. And so they're dependent on those pteropods and those species. Well, living pteropod, when placed in high CO2 water, while it's still alive, the shell will begin to dissolve within 48 hours, and the shell will be gone within a few weeks. So this is a significant problem for that ecosystem.
Is there doubt about the chemistry of higher CO2 levels and impact on ocean acidification? Is that...
No, there's no doubt about that, and let me explain why. We have worked at the international level with through the 1990 WOS program, which was the repeat WOS hydrographic survey, with 15 countries working together, collecting over 72,000 samples in the 1990s from surface to bottom along every portion of the ocean, from Antarctica to the Arctic Ocean, from Japan to the U.S. All these countries worked together. The data sets were brought to my laboratory. We processed the entire data set and made all the corrections to the data set and allowed to determine exactly where all the anthropogenic CO2 is going. We did this by determining the changes in anthropogenic CO2 since the pre-industrial, using a combination of observations and models working together. We also had colleagues on those same cruises collecting samples for the isotopic signature of that CO2, and the changes in the isotopic signature were consistent with the increase in anthropogenic carbon dioxide, which has a very unique isotopic signature. And that penetration of the anthropogenic CO2 goes down to, for the most part, the upper 1,500 meters of the water column. So most of the anthropogenic CO2 is still in the upper part of the water column, where most of our organisms live. And we know that extremely well. Now, in this decade, it's in 2000, we've been repeating those cruises, so we can see the direct changes to the uptake of carbon dioxide from the atmosphere from the 1990s to the present. And on those cruises, we see the same rate of change of pH that we do at the time series sites at HOTS and BATS. So we know now from the large extended surveys across our oceans that we are seeing the exact rate of change of pH in CO2 increases in the water column. This is known extremely well. There's no debate about that at all.
I think I'm way over time, Mr. Chairman.
Thank you. I'm not sure if it'd be Dr. Bartlett or Mr. Rohrbacher. Mr. Rohrbacher. Thank you, Dr. Bartlett, for your...
Well, thank you very much. And for the record, I'd like to place in the record a... Can you hear me now? Okay. I'd like to place in the record a portion of President Eisenhower's farewell remarks to the country, in which he warned about what happens when science and politics gets too intertwined and government grants become the goal for various researchers.
Will that include the military-industrial complex portion?
That is exactly right.
I understand. I've read the whole document. I would never object to Mr. Eisenhower being entered into the record. He has some other interesting
comments. What the public needs to understand is that Eisenhower equated the threat of the military-industrial complex similarly with intertwining science and the government. All right. Dr. Alley, with all due respect, you didn't answer the chairman's question. You know, the question was a very good question. There have been these back and forth between on glaciers and the melting that we've seen over and over again. Why did it happen then if these same factors that you're blaming it on didn't exist then?
I can give you as much or as little answer as that you would like.
Give me 15 seconds.
Okay, give me 30 if I may. The ice ages are caused by features of Earth's orbit. Your brightness is the sun. This is the Earth.
Right.
This is the equator. Here is the North Pole.
Yes.
If the North Pole stood straight up, you could never give me a sunburn on my bald spot. But in fact, as you know, it is tipped over a little bit, and it nods a little more and a little less over 41,000 years. Now, when it nods more, my bald spot ice melts, and the equator is a little more shaded, and now the ice grows, and now the ice melts. But it takes 41,000 years for this change to happen. We know what that's doing right now, and it's not fast enough to explain what we're seeing.
Tell me all of the other melts and backs and forth took all those thousands of years. There wasn't a situation where on Mount Kilimanjaro you had it 10 years you had this much ice and then the next year you didn't, and vice versa.
Kilimanjaro, the records are fairly short. It would be not the best one to lean on, unfortunately. You know, what you do with glaciers, and I hoped I had made that point, is that one glacier can do interesting things. The world's glaciers tend to listen to the climate, and so you need to take a large data set of glaciers to know what's going on.
We all know that these things happen. The major question of this whole debate today, and I'm very grateful to the chairman for bringing this and having an honest exchange of ideas, is what role mankind is playing, and thus if mankind is playing a minor role, how does that then justify some of what we consider to be draconian solutions in controlling human behavior that has been offered to us by people who are espousing this particular theory? Mr. Santer, let me ask you this. You said, I think it was you who said, the sun, or some people are trying to say the sun explains everything. No, a lot of people are trying to say the sun explains a lot. Maybe you could explain to me why we've noticed that there are similar trends of these meltings of the polar ice cap that are going on Mars. If it is not the sun that is a major factor and human activity, why is that?
If I may, sir.
Sure, go ahead.
Mars actually is linked a lot to the orbit as well. It also has some dust storm issues to deal with.
Well, of course it does. But if we have the same thing going on at the same time, and you're blaming human activity for what's going on in Earth, but you see it at the same time on Mars, why do you automatically assume, well, that must be human activity?
If, sir, I wanted to get a measure of how bright the sun was and whether it was getting brighter or dimmer, looking at an ice cap on Mars, which is changing, its orbit has features which change the sunshine, and it has dust storms which change the sunshine. That's a very, very indirect, imprecise measure when we have very precise satellites that you paid for, the people paid for with their taxpayer money, which are measuring it and show no increase in the sun's brightness.
Okay, yeah, you'll have to correct me if I'm wrong, because I am not a PhD.
Mars is a bad solar sensor, and then the satellites are actually very good solar sensors.
Well, but if you have a situation on Mars that you have that situation, is it just when people talk about solar activity, are we just talking about the brightness? Are we talking about other type of solar activity that has an impact on not human climate, but the climate of this planet and the other planets of the hemisphere?
It's a very interesting question that you ask, sir, because at some level we know that we see the sunspot cycle and we see a very weak response in the temperature. So we know that the sunspots are affecting the climate, and it actually looks like they're affecting it just a tiny bit more than you'd expect from the change in the brightness. So there is a little possibility of a fine-tuning knob on the sun, which is not just the brightness, it's other factors.
But we do know there's been these changes, because we do know that there was a medieval warming period, even though we can see that there's been attempts over the history of this research into global warming of trying to basically negate the changes that took place between the medieval period and the current period of time. But was the temperature higher on the Earth during the medieval period? Is there any evidence that the temperature got to be as high? And if it did, how could we blame that then on the production of CO2?
Yeah, we have fairly high confidence that it's what we call the medieval climate anomaly, and it reflects a low in volcanoes blocking the sun and a slight high in the brightness of the sun. And the best reconstructions that we have indicate that it is not as warm as what we're having now, but with uncertainties that if you sort of go to the far fringe, it just might be about where you are. Now, this is a very interesting thing you bring up, because nature, you know, when the snow melts and the glaciers melt and then they reflect less sun and they suck up more heat and get us warmer, those positive feedbacks don't care whether we made it warmer or whether the sun made it warmer or other things made it warmer. They just care that it got warmer. So we actually use the size of the medieval as one of many ways to find out how much warming we might get from CO2.
That's the essence of the discussion today.
Exactly,
it comes down to whether or not this has it's Mother Nature or the nature of the universe versus human beings doing something that they now need to be controlled about. Dr. Michaels, before my time is up, I should give you a chance to comment on
that one. Well, I would look beyond the medieval warm period, and I would look at the end of the what's called the beginning of the post-glacial period for several millennia, where we know, based upon fallen trees, when a tree falls in the tundra, or in the northern part of the distribution, falls into an acid environment, and it's saved, it's preserved, so we can date the tree with carbon dating and find out when it existed. We know that the boreal forest, the North Woods, extended all the way to the Arctic Ocean in Eurasia, and in fact onto the Arctic Ocean islands. We know that it has to be about 6 to 7 degrees Celsius, that's like 12 degrees warmer, in July for that forest to exist. That's how much warmer it had to be.
And that's before humankind had any type of impact on this. And let us note this. But let it. Yeah, okay. Let us
it's
note
the orbits.
But let us note this: the actual statistics. When you start your statistics of how much warmer it's getting now, you're starting your calculations at the bottom of a 500-year decline in world temperature, which was the Midi Ice Age. Is that right, Dr. Michaels or Dr. Alley?
Yeah, no, it is very, very clear. A lot of my work is reconstructing the history. Nature has changed climate a lot by itself for reasons that we understand reasonably well, and we know are not active in this one. If we were not here, you know, if humans weren't here, and we didn't care about anything that lives here, if this were a video game, I'd push the button and see what happens, because it'd be really exciting. But it's not a video game.
Well, the reason I brought up the Eurasian Arctic is because, again, it appears it was quite warmer for millennia up there, and the only way you can get it that warm is to run water into the Arctic Ocean that's very warm, and there's only one gate for the water. It's the strait between Greenland and Europe. So that means that the temperature of at least eastern Greenland had to be quite a bit warmer for a very long time. And the integrated warming is probably greater than what we could produce if we tried to burn as much carbon fuel as we could. And the ice still didn't rapidly fall off of Greenland, as some people are saying it's going to fall off in 100 years. Well, it didn't fall off in a couple thousand years.
Central Greenland was about 1 degree warmer, 1.5 degree warmer, based on about 5 lines of evidence that I could summarize for you, and Greenland was smaller during this warm time by something like half a meter of sea level.
But again, the scenario of the rapid loss of ice simply didn't occur, and that's what's really driving the policy on this. It's not the gradual warming that's driving.
For the record, the stenographer here can't record that Dr. Ailey is periodically pointing to the top of his head. And it is actually substantive, because his argument was illustrated by the point that the angle of the Earth relative to the sun can change over time with a bit of a wobble in the axis of the Earth. And the top of Dr. Alley's head presumably represents the North Pole. I will speculate where the South Pole is. But The symbolism is apparently that the Earth tips towards the sun, and that may be accounting for some of these prior periods in the absence of anthropogenic CO2. I want to recognize that.
Which is fine. That
And
doesn't
the polar bear survived, and the Inuit culture
Right.
I
developed.
want to recognize Dr. Bartlett.
Thank you very much. Apologize for my absence. The Chevy Volt is on the mall, and I've been scheduled for quite some time to speak briefly to the group there at the introduction of the Chevy Volt to Capitol Hill. So I'm very sorry that I missed your testimony. You know, in the past, the Earth has been very much warmer. We had subtropical seas at the north slope of Alaska, or we wouldn't have oil there. And there weren't any humans there then, so clearly something else caused it. That doesn't mean that our activities today are not enormously important in climate change, because if you're at the tipping point, if a car is halfway over a cliff and it's at the tipping point and a little baby comes up and pushes on the rear end of it, it's going over, isn't it? So if we're at the tipping point, it's irrelevant whether our contribution is small or great. If we're at the tipping point and we tip it over, we've done it. I had a chart that I'd hoped that the staff could get up on the screen. Can we get that up on the screen? Okay. Oh, and I want to apologize for my question to the first panel, because I know I am a scientist. I know that scientists shouldn't be concerned with policy. But the only reason you're here is because we're concerned with policy. And we would like science to illuminate our policy. And so my question was better directed to other people, you know, regardless of what the science is, whether you agree with it or disagree with it. What the people want to do who want to move to less fossil fuels is exactly the right thing to do for two other very good reasons. We can get that. This is a chart, and this is quite a startling chart, because just a few years ago, nobody would have predicted that we'd be saying this today. Because our USGS was predicting that oil was going to be ever more and more abundant, that the consumption of oil was just going up and up forever. That's in spite of the fact that in 1956, M. King Hubbert predicted the United States would peak in 1970, and we did, right on schedule. There's the chart up on the little screen over there. The dark blue area, here it is on the screen behind you, the dark blue area is conventional oil that we now know about, that peaked in 06. And for the 3 or 4 years before the recession, the production of oil worldwide was static, and demand was going up. With static supply and increasing demand, the price went up $50, $100, $150 a barrel. Then we had the recession, which we should have capitalized on because it gave us a little breather. Of course, we did none of that, and SUVs and pickup trucks are back on the road in grand style in our country. But you look at that chart there, and what they are predicting is, see that light blue area? You know, that is the dream. That is the dream that says that we're going to find enough more oil, or produce enough oil from the sites that we have found. And many of these new sites are deep water sites, enormously difficult to get at, enormously expensive to get at. I don't think that there's even a prayer that we're going to come close to producing as much oil as they say we're going to produce by developing the fields we now know and finding new fields. If you look at the oil chart and the discoveries of oil, most of them were in the past. The new oil that, by the way, a large discovery of oil is 10 billion barrels of oil. Every 12 days, the world uses 1 billion barrels of oil. That's pretty simple arithmetic. About 84 million barrels a day, 84 goes into 1,000, roughly 12 times, doesn't it? So if you have a 10 billion barrel discovery of oil, oh, you breathe a sigh of relief. It's all over, guys. We got oil. 120 days. That will last the world. Big deal. So, you know, what we're trying to do, I know that scientists are concerned about science, and I am a scientist, but we're concerned about policy, and the only reason you're here is because we want you to illuminate our policy. And whether you agree with my colleague that we're a major factor in this or not is totally irrelevant, because the right policy is to do exactly what people want to do. If you believe that human activity is increasing CO2 and changing the climate, you want to move to fossil fuels. That's exactly the same thing that those who are concerned about national security want to do. We have only 2% of the oil. We use 25% of the oil. We import 2/3 of what we use. Exactly the same thing that people want to do who recognize. By the way, the first person to recognize this was Hyman Rickover in 1957. Pull up his speech. Just Google. You can find the link on our website, or do a Google search for Rickover and energy speech. And one of the really important things he said in that speech was that how long the age of oil lasted was important in only one regard. The longer it lasted, the more time would we have to plan an orderly transition to other sources of energy. And I'll close, Mr. Chairman, by noting that we in this country have now blown 30 years. We knew of an absolute certainty in 1980 when we look back to 1970, which was when M. King Hubbard said that oil would peak in this country. We knew of an absolute certainty that he was right about the United States. Now, we tried to make him out a liar by doing a lot of things. We've drilled more oil wells than all the rest of the world put together. We have found oil, a lot of it, in Alaska and the Gulf of Mexico. But in spite of those things, today we produce half the oil, less than half the oil, we did in 1970. He predicted the world would be peaking about now, and we are. And so, you know, if the policy we're looking for is whether or not we ought to be moving away from fossil fuels to alternatives, absolutely. Just one more word. There are two kinds of energy that we use, electricity and liquid fuels. The future will have all the electricity that we need. With more nuclear, France produces 80% with nuclear. With more wind and solar and micro hydro and true geothermal, that's not your heat pump looking at 56 degrees rather than 90 degrees in the summer and 10 degrees in the wintertime. We'll produce as much electricity as we'd like to use. The real crunch is going to be liquid fuels. If you're wildly optimistic about every one of the possibilities for liquid fuels, they don't alternatives, they don't even come close to 84 million barrels a day. Two bubbles have already broken. One is the hydrogen bubble. Have you ever heard anybody talking about hydrogen anymore? They finally figured out it's not an energy source. It's just the equivalent of a battery that carries energy from one place to another. Real clean when you use it, you get water when you burn it. The second bubble that broke was the corn ethanol bubble. National Academy of Sciences says if we turned all of our corn into ethanol and discounted for fossil fuel inputs, silly to pretend you're displacing fossil fuels if you're simply using them in another form, we would displace 2.4% of our gasoline. This is not Roscoe Bart, this is National Academy. They further said, and this is their statement, that we would save more gas than we would by turning all of our corn into ethanol if we just tuned up our car and put air in the tires. Now, the next bubble that's going to break is going to be the cellulosic ethanol bubble. We will get something from biomass. It will not even come close to what they hope to get. The life on this earth is dependent largely, except what comes from the sea, on about 8 or 10 inches of topsoil. That's topsoil because it has organic material in it. This year's weeds grow largely because last year's weeds died and are fertilizing them. We can, for a short period of time, rape the topsoil and get away with it. What is the sustainability of cellulosic ethanol? That's the next bubble that will break. We just have to come to the realization that fossil fuels or liquid energy and the amounts that we would like to use it just aren't going to be there. We're going to go largely to an electric world. Electric cars, you can't electrify the airplane, by the way. And big trucks won't run on batteries very well. So we're going to have a very, and this is a very challenging future for me, Mr. Chairman, because every 6 hours we go another $1 billion in debt, and every 12 hours we have another $1 billion trade deficit. The jobs that went overseas aren't coming back, so we've got to create new ones. And my dream is that we can create those new jobs in the green area, and we can once become a major exporting country. And this committee is going to be very important in that regard in sponsoring the basic science that will make this green technology important. I'm sorry I ran over my time, but this is something obviously that I'm kind of passionate about. And thank you very much for holding the hearing.
One would not detect the passion. Dr. Bartlett, I appreciate the eloquence and the sentiments and echo them myself. I share them, and as I mentioned at the outset, you've embodied them in your own choices about how you power your own life, and it's admirable that you do. One last question for Dr. Feely, if I may. One of the concerns that many of us have about this phenomenon is to what extent are we making decisions now that put us well down the road of a long-term impact, even if we make changes today? And so the sort of at what point do we start bending the curve in the right direction? My understanding is that well, enlighten us. To what extent is the CO2 already present going to cause problems for the ocean?
That's the exact question that the scientific community is wrestling with right now. And there's already evidence from looking at organisms in seawater that we already see we've already had an impact. 4am shells are getting smaller. You can compare shells that are collected at present with living organisms to what shells that were on the bottom of the sea from 200 years or longer ago. There's a significant difference. So we already know that we're having impacts. We know with our own shellfish industry on the West Coast that we're having significant impacts. Have we reached a tipping point yet? This is the question we're really asking ourselves, and it's very hard to answer that question. What we do know for sure, if we get above 450 parts per million, we'll cause the Arctic Ocean, the Antarctic Ocean to go corrosive top to bottom. That's a tremendous impact.
Say that again. To go corrosive?
Corrosive from top to bottom throughout the entire water column.
Corrosive to the marine organisms.
To the calcifying organisms, which means that the pH would be about 7.7 or so. And consequently, that's not too far away, and we have to begin to concern ourselves of whether or not we would go much farther in terms of CO2 levels beyond that, which would impact large areas of the Pacific and Atlantic Ocean. You know, the projections out to the end of the century say that we would have CO2 levels as high as 800 parts per million, which would have impacts for the entire Southern Ocean, would impact the coral reefs throughout the world oceans, and would even impact our deep water corals, which we know very little about.
So let me just make sure I understand. At current rates of increase of CO, we're already having problems at current rates of CO2 in the atmosphere. At projected increases with economic development, et cetera, if we don't change, as Dr. Bartlett's been talking about, if we don't change our energy system to a less fossil fuels-based energy system, the projected levels could reach levels where in the major polar regions and elsewhere in the oceans, the water itself would become corrosive to the organisms that have evolved over many millions of years to live there, and the base food chain for much of ocean life could be significantly impacted. Is that a fair statement?
That's absolutely correct.
Now, this highlights something that's fundamental to this hearing, and it is this. And it goes back to my friend Dr. Bartlett's analogy. If your car might be at the tipping point, and there's some uncertainty about that, do you tell the baby to stop pushing? It just seems to me if the car is going to go off the bloody cliff, if there's doubt, you stop pushing. Especially when the solution can be beneficial to your economy, beneficial to your national security perspective, beneficial to your environment, beneficial to human health. Why not stop pushing, for goodness sakes? If there's doubt. And Bob Inglis had the example earlier of the analogy. We have been bent over backwards on this committee and this hearing today to include folks like Dr. Michaels, Dr. Lindzen. But the reality is, surveys of top-flight scientists have shown the majority suggest that there is real reason for concern. And if there's real reason for concern, should we not tell the baby to stop pushing if we have ways to do it? And so I thank this panel. We're now going to talk further about what possible impacts might be. I thank the panel. It's been a spirited discussion, a constructive one. And again, as I've done before, for folks who, please, Dr. Bartlett.
I cannot stay, but I would like to note that the importance of these hearings is not the fact that some congressman is up here listening to you. The importance of this hearing is that it's on the record. And so thank you very much for coming. The next panel will be on the record. I really regret that I can't be here, but my chairman will ask the questions that I might have asked and do it better than I.
Well, Doctor, I can't do it better than you, I'm sure, my friend, but one thing I am certain of, and I was going to say, you anticipated it, the transcripts, the written transcripts, the oral transcripts, the video of this will be on the record. So people can actually access the website if you can't sit through the whole thing, you don't want to. And having had the privilege to read all the transcripts, I note, for example, Dr. Cullen, I think, left. If you want to get a really marvelous, understandable grasp of the history of this, I think Dr. Cullen's testimony is just spectacular in that regard. And all the others are. Some of it's, frankly, too deep for me and others, but you'll get the sense, and I think it's good. And Dr. Bartlett, thanks. With this, I thank our panelists for their presentations today and their years of scientific work. We'll take a 5-minute recess, followed by the final panel.
Sorry? Sure.
back out playing soccer, and it's been sitting there too long, so I'm trying to make it straighten up. It will give in a minute. So, sorry. There it goes. There it goes. Okay, we got it. Thank you. Oh, thank you. This was a pleasure. Thank you. Chair here if I can.
Okay, so you're...
Hey, Courtney, could you go back and get my glasses? They're in my outer... How are you?
Oh, hi, Gary. How are you? Good to see you.
I'm sorry. Sorry.
Yeah, hi.
Jim Lopez.
William Gill, how
Nice
are
to
you?
meet you, William.
That's what I used to be, but it's okay. It's close enough. Nobody cares.
Yeah, good.
Nobody cares. Yeah, that's fine. Yeah. Okay, yeah. It's this whole weird thing in the Navy
Hi,
between a
I'm
one-star
Judy
admiral and a two-star admiral. And there's...
Georgia Tech.
Don't worry about it. There's not more than 50 people in the entire world that actually know or care about that stuff. It's RADM, but it doesn't matter. It really doesn't matter.
We saw the one-star picture, so we looked it up. I guess we looked at the wrong one.
Yeah, that's what I... Yeah, it got updated. That was an old job. It doesn't matter. It's fine.
$4 a pound.
Hi. Hi, Lisa. Oh, hi. I heard...
More interesting session, I thought I might do. I'm in Montana. I'm the country boy coming down.
I read this. This is the...
Reconvene in about 30 seconds if we can. I know we're having spirited discussion, but let's try to reconvene so that we can hear from our extraordinarily distinguished final panel, whose patience I greatly appreciate, and as do I appreciate that of our guests in the audience today and my colleagues who have, for very understanding reasons, had to depart. But I'm very, very grateful. Again, this is available to members of Congress, their staff, and to the general public and media on our website. And so I hope people will not consider the fact that we have very important and unfortunately timed organization meetings on both the Democratic and Republican side happening as we speak. Again, we did our level best to be sure people were here, and in the process made sure people were somewhere else, which was a misfortune. But the fact that you're all here is what matters the most in my judgment, and the fact that our colleagues who care, and I hope they do care, will have a chance to review all the testimony is tremendously important. And thus, we begin our final panel as soon as I can find the introductory page. Here we go. Again, appreciate the witnesses' presence. Rear Admiral David W. Titley is the oceanographer and navigator of the United States Navy. I love that title. The navigator for the United States Navy. Every time a ship crashes into another ship, it's your fault, right?
Yes, sir.
Mr. James Lopez, Senior Advisor to the Deputy Secretary of the U.S. Department of Housing and Urban Development. Ms. Lopez, thanks for being here. Mr. William Geer is the Director of Center for Western Lands of the Theodore Roosevelt Conservation Partnership. And Dr. Judith Curry, the Chair of the School of Earth and Atmospheric Sciences at Georgia Institute of Technology. Thank you, Doctor, for being here. We will begin our testimony, as you saw. We'll try to limit the initial comments to around 5 minutes, and then we'll follow up with questions. And thank you. We'll begin with Admiral Titley. Thank you.
Well, thank you, sir. Mr. Chairman and distinguished colleagues, I want to thank you for the opportunity to address you today regarding why the Navy cares about climate change and how we are responding to the opportunities and challenges it presents. Rather than read from my written statement, sir, I will provide brief introductory remarks on the topic and invite any questions from you. The 2010 Quadrennial Defense Review, or QD...
You have a stentorious voice that I could hear, but without the mic, apparently, the others do.
Testing. Are we on? Are we on? Okay. Have to be 5% smarter than the microphone. Okay. The 2010 Quadrennial Defense Review, or QDR, and 2010 National Security Strategy both require the Department of Defense to take action regarding climate change by recognizing the effects climate change may have on its operating environment, roles, missions, facilities, and military capabilities. Taking into account this guidance, the Navy recognizes the need to adapt to climate change and is closely examining the impacts that climate change will have on military missions and infrastructure. The Navy is watching the changing Arctic environment with particular interest. The changing Arctic has national security implications for the Navy. The Navy's maritime strategy identifies that new shipping routes have the potential to reshape the global transportation system. The QDR identifies the Arctic as a region where the influence of climate change is most evident in shaping the operating environment and directs the Department of Defense to work with the Coast Guard and the Department of Homeland Security to address gaps in Arctic communications, domain awareness, search and rescue, and environmental observation and forecasting capabilities. There are other impacts of climate change on missions that the Navy must consider, including water resources and fisheries redistribution, shifting precipitation patterns, and implications for humanitarian assistance and disaster relief. The Navy must understand where, when, and how climate change will affect regions around the world and work with federal partners to develop the capabilities needed to ensure readiness in the 21st century. Navy must also be aware of impacts to military infrastructure both within and outside the continental United States due to increased sea level rise and storm surge. The Navy's operational readiness hinges on continued access to land, air, and sea training and test spaces, and many overseas bases provide strategic advantage to the Navy in terms of location and logistics support. Any adaptation efforts undertaken are required to be informed by the best possible science and initiated at the right time and cost. The Navy is currently beginning assessments that will inform Navy strategy, policy, and plans. The Department of Defense is already conducting adaptation efforts through a variety of activities, including 2 Navy roadmaps on the Arctic and global climate change and the leveraging of cooperative partnerships to ensure best access to science and information. For example, the Navy is partnering with the National Oceanic and Atmospheric Administration and the United States Air Force to advance U.S. environmental prediction capability to mitigate the impact of severe weather and answer operational requirements facing our nation. The Navy understands the challenges and opportunities that climate change will present to its missions and installations. We are beginning to conduct the assessments necessary to inform future investments and are initiating adaptation activities in areas where we have enough certainty with which to proceed. Thank you, sir, and I stand ready to answer any question the subcommittee may have.
Thank you very much, Admiral. Mr. Lopez.
Thank you very much. Is that on? No. How about now? Good? Good morning, Chairman Baird, Ranking Member Inglis, members of the subcommittee. My name is Jim Lopez, and I'm the Senior Advisor to the Deputy Secretary Ron Sims at HUD. Thank you for the opportunity to testify today. On behalf of Secretary Sean Donovan and Deputy Secretary Sims, I appreciate this opportunity to tell you how HUD, individually and in partnership with other federal agencies, is working to develop more sustainable, resilient communities across the nation. In fact, we believe that sustainable communities are resilient communities. Before coming to HUD, I worked on climate change issues in King County, Washington State. And over the past year, I've had the opportunity to serve as part of the President's Interagency Climate Change Adaptation Task Force, chaired by the Council on Environmental Quality, NOAA, and the Office of Science and Technology Policy, including 20 federal agencies and executive branch offices. The Council last month released its progress report with charts and a roadmap for federal action on climate adaptation and resilience. The report highlights the need to better understand and prepare for climate change and offers a flexible framework for federal agencies to engage in that important work. The fact is that even if we could halt greenhouse gas emissions today, the scientific evidence, as we have heard today, suggests that the world would still experience changing climate for decades to come. While government efforts have tended to focus on reducing greenhouse gas emissions, climate mitigation, there should be an increasing focus on preparing for and responding to the threat that climate change impacts represent to our social well-being, the economy, and the environment. That is climate resilience. And that is where I'd like to focus my remarks today. I'd like to make 3 quick points. First, as noted above, we must continue to work towards reducing GHG emissions. We must also step up our efforts to prepare for and respond to climate change. Across the country, cities, counties, and states are putting in place strategies to adapt to risks and stresses caused by climate change, such as flooding and extreme precipitation, temperature spikes and urban heat island effects, water shortages and drought, and rises in sea level in coastal communities. Second, there is a growing recognition that if we are to make progress on climate change, we need to focus on the built environment. That is, on where we build, how we build, and how we move people and goods to the places we live, work, and play. And third, it's important that we tackle climate change in ways that respect and protect the most vulnerable populations, infants and children, pregnant women, the elderly with chronic medical conditions, low-income households, and outdoor workers. And I am pleased to report to you that the federal government is paying attention to climate resilience. Federal agencies are supporting local efforts to adapt the built environment to these new challenges and to protect vulnerable populations through innovative programs and partnerships. In HUD, we have formed an unprecedented partnership with EPA and DOT, the Partnership for Sustainable Communities, which will, we hope, result in reduced carbon emissions as we draw attention to the benefits of more compact, walkable, and climate-friendly communities. We also hope to show that resilient, sustainable communities are resilient communities, as HUD requests for proposals explicitly encourage communities to address climate adaptation and resilience as part of their regional planning efforts. Another important component of HUD and the federal government's work to support sustainable communities is in the area of energy efficiency and green building. Properly implemented and maintained, investments in energy retrofits can significantly reduce energy use in existing buildings, improving comfort for residents, and lowering carbon emissions. Let me conclude by briefly touching on what we were doing to foster similar cooperation between federal agencies on climate adaptation. The Interagency Climate Change Adaptation Task Force, of which HUD is a member, submitted a report to the President emphasizing the importance of this issue to the federal government. President Obama signed an executive order in October 2009 that called on the task force to recommend how federal agencies could play a role in a national climate change adaptation strategy. In the progress report we released last month, we reaffirmed the Obama administration's commitment to mitigating greenhouse gas emissions and, in the long term, to improve our ability to manage the impact these emissions have on our lives. Mitigation and adaptation are inextricably linked, and both are required in order to reduce the impacts of climate change. The task force recommended in its progress report that federal agencies make adaptation a standard part of strategic planning to ensure that resources are invested wisely and that federal programs, services, and operations remain effective in a changing climate. In short, the federal response is rising to the level of the challenges before us. Thank you, Mr. Chairman. I look forward to answering your questions.
Thank you, Mr. Lopez. Mr. Gear.
Thank you, Mr. Chairman. With the other participants, we appreciate the opportunity. Can you hear me better now? We appreciate the opportunity to stand before or sit before this committee and share the concerns we have on climate change and cite what we are doing about it, what we see in the field, what we're doing about it. I have no PowerPoint slides. But I represent a community of people, both professionally and in terms of passion of use, that have a great concern about what's happening in environmental change. Professionally, I represent fish and wildlife biologists. I've been one for 38 years. And so I've had a chance to work on a lot of impacts and a lot of development projects, and I've seen changes. I don't always know the causes of all those changes, but the people in my field always have to deal with the consequences and manage accordingly, even if we can't always decide where exactly did that change come from. And in terms of the passionate users, I represent hunters and anglers. Many of these hunters and anglers are not scientists, some in fact are, most are not, but they have a passion for use of the resource, and we often feel that they also are some of the first observers of change in a field. They see things in a natural environment because it affects the distribution of animals that perhaps they pursue hunting and fishing. And of course they want us to do something about it. I live in Montana where about half the population actually hunts and fishes. 20% still hunts and about half of them hunt and fish. And that's a sustainable outdoor recreation economy in a state of less than 1 billion people, of over $1 billion a year. It's economically pretty significant. And I meet frequently with these sportsmen in more than 32 cities scattered around the state on a regular basis. I talk about many conservation issues, climate change being one. And what I found over the past few years in talking about climate change, that while some sportsmen won't utter the words climate change, it's partisan right now, and it's almost a toxic phrase, most of them will readily acknowledge that the shorter winters, reduced snowpack, increasing spring rainfall, lower stream flows, melting glaciers, a mountain pine beetle epidemic reflect an environmental change that does not bode well for fish and wildlife or hunting fishing as recreational activities. As a consequence, in 2008, 9 of the nation's leading hunting and fishing conservation organizations released a book called Season's End, a report predicting the impacts of climate change on fish and wildlife habitat and its implications for sustainable hunting and fishing. And some of the conclusions are, based on the best available predictions from scientists we heard earlier, that upland birds face disruptions in life cycles that will sever reproduction and the emergence of critical food resources. In cold, wet springs, young birds sometimes suffer fatal exposure to cold from loss of thermal snow cover, with reduced nesting success leading to losses in specific age classes and eventually to population instability that, coupled with increased predation and an influx of invasive species, result in fewer birds in the hunter's bag. In Montana, though, we have some complications because climate change isn't the only stressor on the landscape. We find that, for example, sage grouse declines have also been tied to natural gas drilling disturbance too close to leks and brood rearing areas. So we have to integrate many sources of stress on a resource and try to manage around them and be successful. There are species like mountain goats and bighorn sheep that have a much more narrowly defined habitat and are much more sensitive to a changing climate. They will have to compete for increasingly isolated, fragmented, and diminished habitat. Rising temperatures in the Rockies potentially will allow trees and shrubs to overwhelm sagebrush ecosystems that now provide desirable winter forage for pronghorn elk and mule deer. And big game hunters in Montana are already having less success because winter snows are arriving later in the fall, keeping elk and mule deer at a higher elevation and less accessible areas through most of the hunting season. And it's not just a matter of we enjoy hunting. Hunting is a necessary management tool, and if you're in the business of managing wildlife, many of our hunts are based on population management and migrations downhill into areas where people can get to provide the hunting necessary to provide herd size management. Shorter winters will affect the availability of waterfowl food and cover and quality of habitat. Longer ice-free seasons will lead to changes in migratory timing, routes, and wintering locations. Sea level rise on the coast certainly will inundate coastal wetlands and squeeze waterfowl into narrowing bands of habitat. And the prairie pothole region, of which Montana is part, could lose up to 90% of its wetlands, small wetlands, to climate change, and reducing the region's breeding ducks by as much as 69% in an area that we call America's duck breeding factory. And hunters throughout the country now report that waterfowl migrations are occurring later in the season, and in some cases not occurring at all. Warming waters will slow trout growth rates, increase stress and susceptibility to toxins and parasites and disease. Trout will be forced to congregate in constricted habitats and compete with invasive species. Non-native smallmouth bass have already moved 40 river miles upstream in the Yellowstone River, displacing Yellowstone cutthroat trout, a very cold water species, because of warming water. The physical habitat was there, but now the water's warmed up. There's lower June runoff, lower August precipitation, lower August flows, water warms up, we change the species mix. The declining stream flows with less snowpack have already decimated fishing opportunities in some western states, where trout populations could be reduced by up to 50%. Trout fishing spots and success will change significantly, and mostly not for the better. Climate change could fundamentally change the participation rates of America's 13 million hunters and 28 million freshwater anglers, as fish and wildlife habitat, abundance, and distribution shift in response to a changing climate. Patterns of recreational activities will shift as well. The loss of big game and upland bird hunting opportunities in Idaho, Montana, and Wyoming, the northern Rockies, would impair a sustainable recreational economy that currently supports more than 4.3 million hunter days annually and generates more than $3.45 billion annually in economic value. Nationally, outdoor recreation, including hunting and fishing activities, contributes 6.5 million jobs, pretty necessary in today's economy, and a total economic value of $725 billion per year. We have another new report. Now, it's not just a matter of reporting impacts, but what are we going to do about it? We're in the business of doing adaptive management, and we presented ideas and adaptation strategies, which we distributed in a book called Beyond Season's End yesterday to the committee, in which we identify candidate types of strategies and projects that we could do, and along with a likely cost, to help alleviate and ameliorate the effects of climate change. There's going to be species that win and species that lose. We can't change the climate necessarily. We're not the greenhouse gas emission experts. What we specialize is in how do we adapt to what's left. The report gives numerous examples of what can be done underground, real-world stuff to restore and protect crucial habitat for waterfowl, warm and cold water fisheries, big game and upland birds, and saltwater fish, and to secure connective corridors between habitats, allocate water for sport fish, adjust population management and harvest, and develop state and national adaptation plans. We already have some mechanisms that you fund through Congress called state wildlife grants, state wildlife action plans. They're now landscape level that will help become fundamental tools for managing landscapes of changing environment in the field. And we estimate that the cost of such an adaptational plan nationally is likely at the start to be in the neighborhood of nationwide of $1 to $3 billion a year. But we think that the consequence of not taking action now is going to be much more expensive in the future. It will have economic consequences to the economy, and certainly the quality of living for our children and grandchildren are going to be affected. I have one statement I'd like to make, one sentence I thought was pertinent, that economists made back in March, not biologists like me. And I think it reflects today's attitude somewhat. Action on climate is justified not because the science is certain, but precisely because it is not. Thank you.
Thank you, Mr. Geary. Dr. Curry.
I'd like to... Hello? Okay. I'd like to thank the chairman and the committee for the opportunity to participate in this hearing. You've heard forceful arguments from climate scientists for a looming future threat from anthropogenic climate change. Anthropogenic climate change is a theory whose basic mechanism is well understood, but whose magnitude is highly uncertain. This conflict regarding this theory is over the level of our ignorance regarding what is known about natural climate variability, about what is unknown about natural climate variability and the feedback processes. Based on the background knowledge that we have, the threat from global climate change does not seem to be an existential one on the time scale of the 21st century, even in its most alarming incarnation. It seems more important that robust policy responses be formulated than to respond urgently with policies that may fail to address the problem and whose unintended consequences have not been adequately explored. How to deal with this complex problem presents many challenges at the interface between science and policy. Over the past 20 years, scientists have become entangled in an acrimonious scientific and political debate where the issues in each have become confounded. Debates over relatively arcane aspects of the scientific argument have become a substitute for what should be a real debate about politics and values. I have been publicly raising concerns since 2003 about how uncertainty surrounding climate change is evaluated and communicated. At this point, it seems more important to explore the uncertainties associated with future climate change rather than to attempt to reduce the uncertainties in a consensus-based approach. It's time for climate scientists to change their view of uncertainty. It's not just something that is merely to be framed and communicated to policymakers while mindful that doubt is a political weapon in the decision-making process. Characterizing, understanding, and exploring uncertainty is at the heart of the scientific process. And further, the characterization of uncertainty is critical information for robust policy decisions. It's important to broaden the scope of global climate change research to develop a better understanding of natural climate variability and the impact of land use changes. And far more attention needs to be given to establishing robust and transparent climate data records, particularly the paleoclimate record. Regional planners and resource managers want accurate, high-resolution climate model projections to support local climate adaptation plans and climate-compatible development. The need for such models is unlikely to be met, at least in the short term. In any event, anthropogenic climate change on timescales of decades is arguably less important in driving vulnerability than increasing population, land use practices, and ecosystem degradation. Regions that find solutions to current problems of climate variability and extreme weather events and address challenges associated with an increasing population will be better prepared to cope with any additional stresses from climate change. Climate researchers need to engage with regional planners, economists, military intelligence organizations, development banks, energy companies, and governments in the developing world. Such engagement can develop a mutual understanding about what kind of information is needed, promote more fruitful decision outcomes, and define new scientific challenges to be addressed by research. The need for climate researchers to engage with social scientists and engineers has never been more important, and there is an increasing need for social scientists and philosophers of science to scrutinize and analyze our field to prevent dysfunction at the science-policy interface, which has been so evident this past year. Climate scientists and the institutions that support them need to acknowledge and engage with ever-growing groups of citizen scientists and extended peer communities that have become increasingly well organized by the blogosphere. The more sophisticated of these groups are challenging our conventional notions of expertise and are bringing much needed scrutiny, particularly into issues surrounding historical and paleoclimate data records. These groups reflect a growing public interest in climate science and a growing concern about possible impacts of both climate change and climate change policies. And further, this interest has illuminated the fundamental need for improved and transparent historical and paleoclimate data sets and improved information systems so that these data are easily accessed and interpreted. We need to identify and secure the common interests in dealing with the climate, energy, and ocean acidification problems. A diversity of views on interpreting the scientific evidence and a broad range of ideas on how to address these challenges doesn't hinder the implementation of diverse bottom-up solutions. Securing the common interest on local and regional scales provides a basis for the successful implementation of climate adaptation strategies. And successes on the regional scale and then national scale make it much more likely that global issues can be confronted in an effective way. Thank you.
Thank you, Dr. Curry. I apologize. Our AV unit, which none of you apparently require, is deciding to cool itself off, perhaps metaphorically. It may be smarter than we think. Thank you all for your testimony. The structure of today's hearing, as I mentioned from the outset, was to talk first about the basic science. Are we seeing impacts, and then what are the impacts of what is happening, and how does it impact our lives? And we've got outstanding witnesses, and what I'd like to do is follow up with each of you sort of on individual themes, but then if there are cross currents to that, please address those. Admiral Titley, you know, I've had the privilege when I've been to Afghanistan, Iraq, and other theaters. You know, there are command daily briefings, and the idea is that the regional commander gets to look at all sorts of things, what's our force strength, what's our available mobility, et cetera, et cetera. One of the key elements of that is always weather. You know, are there going to be dust storms? Are there going to be clouds? Can the drones see what their targets are? Will we have air cover, et cetera? It must be especially acute in the Navy for your mission. And what occurs to me is you would be irresponsible as a commander if you did not take into account weather changes. The things you've talked to us today about, including the infrastructure commands, the changing potential in sea lanes, available access to ports, et cetera, that's a longer term frame. But would you not be equally irresponsible if you didn't look ahead to that and try to make long term strategic plans, not just tactics, but strategy on the ground? Elaborate on how the Navy views this issue.
Yes, sir. I'm not sure I can say it much better than what you did, but at the risk of going downhill from here, I will try. You're absolutely right, sir. I've done weather forecasting in the Navy now for over 30 years. It starts off sort of at the unit level or the tactical level. We look at both the safety of the forces. Really, you know, the Navy has learned that really from time immemorial going to sea, but certainly in the typhoon of 1944, Admiral Halsey tragically lost 3 destroyers and over 700 sailors because we didn't know there was a typhoon out there. We fixed that. We have a Joint Typhoon Warning Center staffed by the Navy and the Air Force, and we have not had a repeat of that situation, thank God, since then. As you get more senior, you start looking at operational level. What will the weather and the ocean be in 3, 4, 5 days? Where do I put my units to best have my chance of success? I think Heidi Cullen mentioned that climate is putting the odds in your favor, and that's how I look at the weather. I talk about the weather as we all operate in nature's casino, and I intend to count the cards. The bad news is there's a lot more than 52 cards. The good news is if you can do it, nobody breaks your kneecaps. So that is really what we're trying to do, is to put the odds in our favor. And now, sir, as you absolutely have it spot on, we're looking strategically out. So not just 3 or 4 or 5 days, but what are the next 20, 30, 50 years going to look like? We can see the signal in the Arctic. The observations tell us what's going on. We see that the percentage of what's called multi-year, or the thick ice, has dropped to levels that frankly we have not recorded before. So although 2007 was in area extent the least amount of sea ice that was recorded, and 08, 09, and 10 were slightly higher, when you look at the volume of ice, the volume as of last September has never been lower. So, and I should, in respect to Congressman Rohrabacher, I should not say never. In the last several thousand years, it has not been lower. So we see the probable opening of the Arctic. I have told Admiral Gary Ruffhead, our Chief of Naval Operations, that we expect to see about 4 weeks of basically ice-free conditions in the Arctic in the mid to late 2030s. By the middle of the century, we could be seeing quite easily 2 to 3 months of ice-free conditions. That's enough time to allow the transocean shippers, assuming they have governance, search and rescue, charting, insurance, all of those other conditions. But by the middle of the century, that's very, very possible. When I talk to my colleagues in Iceland, Iceland is actively thinking about how do they become the Singapore of the 21st century? How do they become that southern terminus? This becomes a very different ocean and a very different world for our Navy to operate in. So this is just one example. I could talk about sea level. I could talk about ocean acidification. In the interest of time, sir, I'll stop here. But you're exactly right. This is looking at what we believe, not guaranteed, but is likely to happen, and looking at consequences times probabilities and planning for those kinds of situations. And that's what we've embarked on, sir.
That's a very, very helpful summary. A context of that also is, not within frequency, people here on the committee will hear a suggestion that all the money that has been spent on climate change research has been wasted. Well, a fair bit of the instrumentation that has been used to gather the data that leads to the analysis came from defense applications, whether it's satellites in the air, whether it's sensors on equipment. And certainly my hunch would be that down the road you folks will be mighty glad to have those sensors and the data that they've given you as you make your planning.
Yes, sir. The data are very useful. We use data from a wide variety of sources. I'm sure you know, sir, that the submarine missions that we had run not only in the Cold War but in the 1990s, they provide very valuable ground truth observations of how thick is that ice, so we can then calibrate or basically tune our satellites. I'd be remiss, though, sir, in saying if this does not also work in the other direction. The Department of Defense is a big user of the civil structure that in part is appropriated from your committee. We work very closely with NOAA. I have a great relationship with Dr. Lubchenko, and one of the things sort of on the practical adaptation side we are jointly looking at between the Navy and the and NOAA and the Air Force. We also have Department of Energy and NASA involved, is how do we look at a next generation of weather, ocean, ice coupled prediction model so that by the roughly 2020, in about 10 years from now, we can predict that system as a couple, as a whole, and really spanning between weather time frames, say hours to days, out to, say, roughly about 2 or 3 decades. Because as we're planning for our infrastructure, or let's say if you're the Port of New York and New Jersey, you're planning for your infrastructure. You want to be looking at that. There are, for very, very good reasons, there are boundaries in the science community between the weather folks, the oceanographers, the glaciologists, the climatologists. But if you're a decision maker, if you're running a business, if you're running a government agency, with all due respect, you don't really care what those boundaries are. You need an answer. And your answers span these time frames. I wish I'd thought of putting it this way, but the words of Rick Anthes, a former director of the National Center for Atmospheric Research, he said, hey, Titley, what you're trying to do is go between a condition forced by initial conditions, what is today's weather, to one forced by boundary conditions. What is the sun doing? What are the greenhouse gases doing? How we get through there, open science questions, big challenge. But I think it's a great challenge for this nation of ours, and one that will help us as we adapt in a cost-constrained environment.
Thank you.
Thank you, sir.
Thank you very much. Mr. Lopez, I'm intrigued by this issue of mitigation and adaptation, particularly as things apply to perhaps disadvantaged communities. And it seems there are there are multiple factors, but one is not only domestically in the U.S., but globally, a lot of the folks who are going to get, if there are the impacts which are projected, which seems more probable than not, in many cases anyway, if those impacts happen, they're going to impact some of the people who had the least to do with causing the problem and the fewest resources to cope with the problem. Can you elaborate on that domestically within our own socio-demographic span, but also if you have insights into globally how that impacts the world?
Well, I think that's absolutely correct. I think that's of particular concern for us at HUD as we implement our programs and policies. We want to make sure that the populations that we serve we are thinking through adequately about the future stresses that might be imposed on those populations, knowing that the more stresses you have today, the more likely you are impacted to be tomorrow. I think there's a couple of points of insight, focusing more on the domestic side of things, that I'd like to make. And first is, as the Admiral points out, these decisions, they're being made today. It's not like we can wait. Moving beyond the military example, the 100-year flood plan, the management of goods and services, agricultural, economic development, the built infrastructure, which is what we deal with at HUD, we have to make decisions now about the future, and those decisions can't wait. So our challenge is, how do you take that fact and build a system or a process that helps to mainstream or integrate the climate change variable? And I would suggest a couple of things. One, and I think it's endemic to these grants we put out, is to find the triggers. There are those communities that are aware of the assumptions of climate change, but there are opportunities that happen, planning opportunities like the challenge grants and the regional planning grants that we've put out. Disaster recovery is an opportunity where you open up and start to say, okay, what does the future look like when we have to rebuild? Infrastructure investments. When you have to spend $1 billion on a wastewater treatment facility, you want to make the best decision you can. And it's really about learning as much as you can right now about what you need to know about the future. So I really think, Mr. Chairman, it comes down to better decisions. And for us, it's the populations in large measure that you identified. So it's about scenario planning. And it's really about, how do you help communities make a decision most compatible with uncertainty? We know there's uncertainty. Local governments and governments at all levels make decisions with uncertainty every day. It's about making those, the assumptions about climate in those decisions transparent, understanding them better, and making decisions in uncertainty. And one guiding lesson we learned, in my perspective coming from local government to the federal government, is to think on the margin. It's about the marginal cost of what you need to do next. It's not necessarily about building a whole new system. It's about the marginal cost of building the reclaimed water system to the $1 billion investment you already made. And when you reach that point, you can do a cost-benefit analysis based on the margins to see how much you know, how much you understand about the future, and whether or not the investment is worth it. And the final point I make is, you always have to consider the co-benefits. For us, we are acutely aware of where you build, how you help communities prepare for the future. That's what we do. Green roofs, green space, energy efficiency, water, it's reuse, it's conservation. All of these things are co-benefits to decisions that have to be weighed in, I think, when you're analyzing the marginal cost of the decision.
Very well put. I had the privilege of riding on a cross-country flight with Secretary Sims, who I have great respect for, and served our region very well. You mentioned the co-benefits. One of the things that I was so impressed with was the Secretary's analysis of things like health benefits from healthier communities. If we do it right, there's a positive synergy to this. If we preserve green space, that, if properly planted, can take up CO2. If we change how roofs are colored, that can produce greater reflectance, et cetera, and more, and reduce temperature inside homes, et cetera. One of the things I would hope we don't do as a body is those who are antagonistic to the climate change scenario, that they don't say anything that was ever done in the name of climate science we're going to reverse, like sort of analogous to taking the photovoltaic panels off the White House as a statement. Well, if we do that, we're going to roll back a lot of things that have co-benefits in and of themselves, and I think that would be really unfortunate for all of the interests we've heard today. Briefly, I'll particularly direct this to Rear Admiral Titley and Mr. Lopez, but if others want to comment as well, and then I'll get back to specific questions. We've in this committee had significant discussion over whether or not a climate service is needed. If so, what would its benefits be? From Admiral Titley and then Mr. Lopez and then Mr. Garrett and Dr. Curry, what are your thoughts about whether or not a climate service would be useful to you, and what would be useful about it if it existed?
Well, sir, thanks very much for the question. A climate service, I believe, would be very useful for the Navy. It provides, I almost hate the phrase, but a one-stop shop, if you will, or at least a source of both coherent and authoritative data. It would be ideally staffed by people who would be conversant with those data. as well as, of course, machine-to-machine ways of pulling these. We have lots of different places with very good quality that produce various types of climate models. National Centers for Atmospheric Research, Department of Energy has some tremendous programs, academia, etc. As a DOD, I do not want to replicate or duplicate. We cannot spend our taxpayers' dollars doing things that have already been done well, but I need access.
But you need that data.
But I need access, and I need to be able to get it without sort of the hunt and peck method, or whatever we call Google now on the hunt and. Back when you and I were growing up, it would be the hunt and peck.
Yeah.
So having that, probably in one agency. I know NOAA has looked at this, and that would make sense to us. Whatever the committee and the Congress and the administration ultimately decide, but the concept of a climate services would be very, very useful to me.
And the model of that would be that it would interface with a number of other areas like agriculture, conceivably fish and wildlife, conceivably HUD, obviously the defense applications. That's the model that we had in mind, and gather the best. It's not a one-way street. It's not that the Climate Service tells you what's happening. Ideally, the Climate Service gathers information from your resources and expertise and data sets, and it's a synergistic model. Mr. Lopez or any others want to comment on that issue? Mr. Gear?
Yes, from the Fish and Wildlife perspective, we support heavily the establishment of a National Climate Service. We feel that as additional information becomes available on a scientific basis, we need to have that information to make intelligent management prescriptions on specific places around the country geographically. What's pertinent in the Intermountain West, where it's in a relatively arid environment, in a changing climate, may still be different than what it is in the southeastern U.S. And what we need is geographically specific information, the best prediction we can get, so the strategies that we put on the ground are the ones that are pertinent and applicable for that particular area, so we don't waste the money either. So for them to be effective, we need that information central kind of area where we can store the information, we can retrieve the information, we can find out where it comes from, we consult with others, we have a much better information base, we are better informed as professionals, and we can do a more effective job. We think that such a climate service ought to be coordinated among the state and federal agencies. So everyone can, this is a worldwide issue. We can all participate in the data gathering and the data sharing and the interpretation.
Dr. Curry and then Mr. Lopez.
With regards to climate service, I think the fundamental need is really the information system. For example, the sea ice issue that was raised earlier, which of the 12 sea ice data sets that are out there should we be looking at? I mean, there's a bunch of different data sets. The average user doesn't know which one to use. There's no error assessments, and then they look at it and they see sea ice in the Mediterranean, and how are they supposed to interpret that? I mean, these data sets are not
no sea ice in the Mediterranean.
Well, I know, but the data set, but some data sets give it to you there.
Is that true?
Oh yeah.
That was not be a data set. That would be a
certain satellite products. If there's clouds, they will mistake clouds for sea ice, and you can get sea ice in the Mediterranean. So how useful are those kind of data sets?
No.
Okay. But my point is we need to establish authoritative climate data records where people sift through the information, look at the uncertainties, and give somebody one data set that they can use. And,
with some error boundaries.
With some error bounds on it, and we also, it needs to be, an issue of accessibility. People need to be able to search and use the data sets, and otherwise, trying to, even for somebody like me, sometimes trying to get the climate data I need, it's torture.
Yeah.
Okay, compared to somebody who's not even a climate researcher who's just trying to use the data set, we have a very fundamental need for a climate data information system.
So some kind of combination of open source, but with a qualitative filter to it.
Yeah, open source would be an interesting route to go. Yeah.
Mr. Lopez?
Thank you, Mr. Chairman. I think I'd like to stay within the confines of the task force report, part of our charge, and what we're calling as a National Climate Change Adaptation Strategy. And I think a lot of the principles that we've discussed, the need to get information out, the need for a dialogue with the scientific community, a process by which we can evaluate that information and embed it into our mission of each agency and across the federal government and down to the states and local governments would be is part of that process. And I think moving forward, we hope to continue a dialogue with you as we work on that
Great.
group.
Thank you. Mr. Gerald, I want to ask you specifically, I represent an area where hunting and fishing is huge. I mean, the Southwest Washington people love to hunt. I grew up as a hunter. We literally fed our family by hunting and fishing. That was our main source of protein, was venison or elk or antelope or rabbit or duck, whatever. If it moved, we shot it. If we shot it, we ate it. And we ate all of it. And that's the case in a lot of my district. And in addition, the recreational pursuit is tremendously important to people. I had the opportunity to talk to one of the ongoing fights back home is gill nets versus sports fishermen. And I had a long conversation with a bunch of sports fishermen concerned about gill netting, and I think it's a legitimate and important debate. Well, at the end of it, we began to talk about ocean acidification, and these folks really hadn't heard much about it. And it struck me that, we're focusing so much on one issue sometimes. What impact do you see if we have ocean acidification, as you heard Dick Feely testify to earlier, and you lose pteropods, you lose the basic food chain for salmonids, and if you increase the temperature of the water, back home we go nuts providing, appropriately so, providing a shade, etc., for streams and other tributaries so that the salmon can spawn in cool water. What do you see as the combination with more acidic water and higher temperature water on, just say, for example, salmonids, to take one example?
Well, I think it's a fairly simple prediction in some regards. If you have less food, you have a smaller population base perhaps of less healthy fish who are able to go upstream and spawn, the anadromous species, then you have an environment upstream that's not particularly inviting for them in the first place. There are some questions to be asked on whether or not, for example, will the chemical makeup of the water at that time change to the point that do not recognize their homing stream anymore, which will upset their spawning behavior. And if they do find the correct stream, or a stream, will they have a physical environment that still enables them not only to spawn, it's not just the act of spawning, the act of recruitment is you also have to have egg hatch. One of the things, if you've worked in fish hatcheries, we deal in things called degree days. A degree day is 1 centigrade for 1 day. And typically an egg for a salmonid is going to require a little over 300 degree days to hatch. And if you have a species that's spawning in spring, and it's tied to the flow, you have fewer number of days with warming water than a species that spawns in the fall and has colder water for a longer time. But those cycles are timed to not only when the eggs hatch, but what physical environment for the young of the year fish exists at that time. Is there side water for young of the year fish, which are not muscular, they're small, they're prone to being washed away and to be preyed upon by big fish? Are there areas of flow at the time of year that they can escape to so you have successful recruitment, spawning, hatching, and survival of young fish to the next age class so they can go downstream? So it's a whole series of factors. But if you start with the fact that you have fewer fish to move upstream because you have a smaller body of fish in the ocean, and they're poor health, they have physiologically in less suitable condition, you have a smaller population going up, you have a reduced spawn size, perhaps a less favorable environment, a lower recruitment, and you have a decline of salmonid populations. You're talking steelhead and Pacific salmon.
What you've hit upon, it seems so important to me, because when we talk about this issue, sometimes people say to themselves, I hear it a lot, wait a second, you're talking 1 degree, 2 degrees. My understanding of the biology of many species is that they many of them live fairly near the upper bounds of their temperature tolerance. And a 1 degree change in water temperature over a period of time can be lethal. A change in pH level can be lethal. Integrated, they can have a terribly negative synergy. And now you're adding in all the other variables about stream flow, other habitat issues, nutrition supplies out, etc. Even small changes can produce those impacts.
Yeah, depending on where they are on the tolerance curve. If you have something, for example, like rainbow trout, that if you're looking Fahrenheit, they have an optimal temperature of 55 degrees Fahrenheit, you have some wiggle room on either side where you can still have either good growth or slower growth and a viable population. But when you get up 5 degrees or something, you're getting to smallmouth bass range, suddenly you have you have physiologically less adaptable fish, you have lower reproductive success, and you have the opportunity for what we're calling invasive species that don't normally belong there, intruding on their territory, which is what's happening in the Yellowstone River, the Clark Fork River, the Bitterroot River, and some other areas. You have species that are more competitive, that operate in a higher temperature range. When you get on the upper edge of the thermal tolerance, that's when you get the higher level of risk. But one of the things I've noted over the years is sort of a general observation, though, that as humans we tend to think as the center of the universe, and we tend to think that what we understand is really what's important. We confuse lack of understanding with lack of importance. We don't understand how a small temperature difference can make a large difference to something else where it may not to us. We're in an insulated environment. We're in a comfortable room with a thermostat controlled, comfortable. Well, if you're outside living in the environment without a thermostat, things are a little bit different. And they don't respond to the same stimuli that we respond to. And one of the things we work in animals, we can debate, for example, whether or not the science is exactly right, whether or not they're at the upper end of the thermal tolerance or whatever. We can debate the policy outcomes that come out of this and even the range of the economy. But the animals don't get that vote. They go to where the environment is within their life history and their tolerance, and if the habitat's not here, if they're mobile enough, they'll go to where it is. And some of them will not enjoy that advantage. They're already at the limits of their tolerance, and there's nowhere else to go. If you're a mountain goat, where do you go? You're already at the high end. So they go to where the habitat suits them, and if it no longer suits them, then we have a decline in the species.
And they don't have time to evolve, to adapt at the pace of change.
No, at the pace that we're changing things right now, we're talking evolutionary changes, simply maybe hundreds of years or perhaps thousands of years. But we're talking things that are going to change much more rapidly, and they simply haven't got time to physiologically adapt in many cases to the environment that we predict may occur. And I hope that we're all wrong, actually, and that we've overestimated that. But the odds aren't looking good.
Yeah. Dr. Curry, I was intrigued by one of your observations I thought was very telling and I think important. It's not just CO2. There are other factors. Yeah, if I caught at least two of them, population and land use. Those are also integrated, however, with CO2 output. Can you elaborate? I mean, they combine to have combined effects. Can you elaborate on that somewhat?
Well, our vulnerability to global warming is largely associated with ever-increasing population, where we choose to build, and what we do to our ecosystems and how we engineer our, and we get rid of some of our barriers. At the same time, as population increases, this is, a big part of the carbon dioxide problem. So it's a big, complex, wicked problem that's coupled in very complicated ways. And again, I tried to make the point that there's no silver bullet solution, and there's all these intersecting problems. I mean, the climate problem doesn't stand alone. It's coupled to population, it's coupled to energy, increasingly to ocean acidification, and we need to look at the broad solution space, possible solution space for all these issues and try to figure out what makes sense.
This population issue seems so important to me because if each individual has their own personal carbon footprint, if you will, the popular term, but basically what it takes for you to live your lifestyle, add a lot more people wanting a more carbon-intensive lifestyle, you just magnify the impact.
Okay, and the population, where the population is growing is in Central and South Asia. That's where the rapid population is growing, and this is where economic development is huge. And what's going on there is going to totally dominate, well, it's already dominating the CO2 story, and it's going to explode, really, in terms of dominating the carbon dioxide situation. And so that becomes a whole political issue about, what India and China does and how we deal with risk. And the whole issue of who's a winner and loser, again, North China looks a lot more favorable in a warmer climate, potentially, okay, with more water and a nicer climate, during part of the year. And so what is going to be their motivation? We haven't really looked at, the winners and losers part of this story in the way that we should and really understood vulnerabilities. I mean, in the U.S. we have a fairly good sense of it, but in a lot of the developing world that are either very vulnerable or like India and China and South Asia that are going to be the big powerhouses in terms of emissions and populations, we just really haven't done a lot of the analysis that we need to do to really sort this out.
What about the argument that, well, there's so many Chinese, so many people in India, Indonesia, et cetera, they're going to pump out so much CO2 that what we do here doesn't matter?
Well, superficially it doesn't, but the Chinese have already poisoned their environment in pretty serious ways. So their big motivation for doing something about it is really trying to stop the poisoning of their soil, water, and air. Okay, so that's their motivation. And on one hand it doesn't, but everybody's going to need there's no way that the developing world is going to be able to compete for like petroleum, in terms of dollars, especially when we see what's, peak oil or whatever. So there's going to have to be alternative energy sources of some sort, and the people who takes the leadership in that area is going to be less vulnerable to price swings and global security issues and whatever. So there's a lot of motivation for being out there in front and taking a leadership position on all these alternative energy strategies.
One final question for you, and then I'll bring it to a close, I suppose. I had the opportunity in almost every case here to look online at other things you had done, and you mentioned the blogosphere. I'll tell you, I was pretty troubled by it. I went on a few climate sites on both sides, and it was not the scientific dialogue that I'm trained in. It was snarky, it was non-substantive, it was ad hominem, it was juvenile, and it was unconstructive.
A lot of it is, okay, but there's what I would call the technical climate blogs that have spun up, and these are people who have an interest in analyzing the data and looking into the science, and people from both sides of the debate show up. So some of the more high-profile ones are very snarky and polarizing, but the blogosphere has sort of developed this sort of lukewarmer technical blogging community where people are actually looking at the data, debating scientific papers, people from both sides in a fairly civilized way. And so I view this as something that it's important to tap into and acknowledge this interest, and there's potential for reducing polarization.
Somehow there's got to be, I mentioned at the outset, and I know you've written on this, I mentioned at the outset this issue of science integrity, and we literally wrote it into the America Competes bill. Now you can't get an NSF grant, but you can blog with nothing. How do we, it's an important point, and the reason it's so important is, and the reason we're having this hearing is to try to say, look, this idea of science by ad hominem attack, by politicization, by false accusations, by conspiratorial theory, by labeling things hoaxes, that ain't science.
I know it's not. But it's going to happen whether the blogosphere is there or not. I'm just saying by engagement, a lot of it, so many people distrust climate scientists and climate science. I mean, they viewed them as arrogant and whatever, and they were worried about UN policies taking over everything, and they were sort of scared. And then when ClimateGate struck with the emails, then people really had more of a concrete reason that they felt not to trust scientists.
Would you say that though obliterates all the legitimate data that we've heard today?
It doesn't at all, but it's an issue of the public trust. And a lot of things like the IPCC assessment report, there's a heavy dose of expert judgment in those conclusions, and if you don't trust the experts, what are we to make of their judgment? So the data and the fundamental research is there. It's how it's assessed, communicated, and by whom then becomes an issue.
This is helpful. I thank you all. I'll share an anecdote occurs to me. Some years ago, I was climbing Mount Rainier, and Rainier, we were going up in the springtime, it's early, and these wicked whiteouts happen. And if you've never been in a whiteout, it's really quite an experience. You literally have no sense of vertical, up or down, and we're walking with ski poles in front of us so we don't walk off something. You're literally sort of probing because you can't see the earth. It's bizarre. And I had the good fortune and maybe good sense to actually, when we left this hut at Camp Muir, to actually take my compass out and take a compass reading. And so we follow this compass reading. Everybody else is just walking the way they think we should walk. And I had the compass reading. And at some point I said, I just don't like the feel of this. We haven't come back across the trail I thought we should have, and our intuition says we should go this way. If we're wrong, I knew from many climbs previously, there's about a 1,500-foot drop down to the Nisqually Glacier. Now I said, maybe what we ought to do is gather together and check our instruments. I happened to have an altimeter with me and a topo map. It was mighty handy. So I had the topo map, I had the topographic map, I had the altimeter, and I had the compass reading from where we'd gone. Everybody else in the party pretty much was saying, we're going to go this way, we're sure it's this way. And I said, well, here's the point on the map where my instruments tell me we are. If we walk another 200 meters this way, I think we walk off a 1,500-foot cliff, as many others have done in equal conditions. The alternative, unfortunately, because we had gone this way this far, was unpleasant. We had to actually go uphill, and when you've climbed all day and you've got a heavy backpack on and it's deep snow and it's spooky and you don't want to go back uphill. You hate it. It's hard work. You're tired. It's not what you want. Relative to a 1,500-foot downhill, well, we trusted the instruments because I had them, and we walked back, and I've never been so happy in my life to see some spilled Gatorade on the snow about a half hour later. We had to literally almost change direction, walk uphill. The instruments gave us the data. And we could have gone where we wanted to go, where it seemed easy to go, where our intuition and our experience seemed to suggest it would go. But the data suggested something otherwise, and we followed the data, and I probably wouldn't be here today because I was on the sharp end of the rope. The point of our hearing today, and I think the point of this committee, I hope, which I am loath and sad to leave, is that we have an obligation to approach decision-making in a constitutional democratic republic with rational, empirical judgment and information. Imperfect and uncertain, but the best we can do. And the hope today was we had a model of how that can happen. We won't reach any conclusions. I don't think anybody's going to say, well, dang, I was a complete skeptic before, now it's turned. Maybe some will go the other way. But the process that we try to follow, and the process of science is what's going to get us there. And I would hope that that process, that legacy, on this committee, if no other, is one based on empirical decision-making, mutual respect, critical analysis, objective analysis, and I'm grateful for the witnesses on all sides that have helped us put this forward. And I hope, for the sake of the 2 5.5-year-old boys on which I make every fundamental decision in my life, and countless others that are dear and dear to you, that we will weigh the consequences of inaction or inaccurate action against the consequences of acting in responsible, reasonable, rational ways for the broader good of not only our society, but the globe itself. And the stakes are pretty darn high, and we've really got to get it right. And I thank all of you for being here today, and all of you who are audience for your perseverance and your patience and your expert input. And with that, this hearing stands adjourned. Thank you. Wait, what's that? Oh, sorry. They always remind me of this. With that, the hearing does not stand adjourned. Customarily, there will be 2 weeks allowed for anyone who wishes to enter additional extraneous comments into the record. And with that, thanks. And I would like, finally, to thank the staff on both the majority side and the minority side for their participation in making this hearing and this last session of Congress so successful. Thank you. With that, the hearing stands adjourned.
That was really great. Okay.
Special Agent Gibbs, I didn't know the new director was punishing you. She always seemed very fair to me.
Well, you're a woman. She doesn't have anything to prove to you.
How about you?